All right, thank you, Michelle. And thank you all for being here for the second day of the tutorial. As Michelle said, my name is Amr Kamil. I'm visiting faculty at Lawrence Berkeley National Lab, and I'll be presenting about UPC++, which is a C++ library for asynchrony and distributed applications. And just a heads up, we did the 20-minute intro session yesterday. I'm not going to repeat everything that was in that intro session. So if you missed it, or if you want a refresher, please go back and take a look at the slides, which you can get to through the main tutorial link. But I will refresh sort of the basics, which is the main features that UPC++ provides is for asynchrony through both one-sided puts and gets, or remote memory access, RMA for short, as well as remote procedure call, or RPC for short, which allows you to move computation to the data, essentially launch some computation to run on a different process. And then UPC++, again, it's a C++ library, but it's designed to be to provide the best possible performance. In particular, communication in UPC++ is syntactically explicit to make it clear what things are expensive in the code and what things aren't. But we also provide mechanisms for asynchrony to manage that cost. So in particular, for instance, we have this concept of a feature that represents some operation that may or may not have completed yet. And I will refresh what that is in a moment. And then finally, we also tried to make the library as scalable as possible, meaning that you can run it on many, many processes, hundreds of thousands potentially. And this was part of the design goals in terms of the mechanisms that we provide to the programmer. All right, a little bit more of a refresher on the two main features, RMA and RPC. So let's start off with RMA. Communication, again, in UPC++ is by default asynchronous. So this means that there's a separate initiation step and then a separate wait step where you can wait for completion. Okay, so in this example over here, if you look at the picture on the right, what we're trying to do is we're trying to read some data using a one-sided get from a remote location. And that remote location itself is represented using a global pointer. And a reminder, a global pointer encodes both the memory address of the underlying object, as well as the process that owns it. So if we want to do a get on this, all we have to do is call the rget function. And again, the global pointer has all the metadata needed for that to happen in a one-sided nature under the hood. But since this is asynchronous, we don't get back the int directly. Instead, we get back this feature object that represents both the underlying int value as well as whether or not it's ready, whether or not that transfer has completed. So once we do the initiation, we can go ahead and do some other work. This can involve doing some more RMAs or doing some local computation or some RPCs. And then finally, at the point where we actually need the value, that's when we can call wait on the future. And in the ideal case, it's already there. And so this doesn't take any time. We just retrieve the value directly. But if the transfer hasn't yet completed, then this will wait for the transfer to complete before giving us back the underlying integer value. So RPC kind of works in a similar process in terms of it being asynchronous. And again, the idea here is that we want to invoke some computation on potentially on some other process. Okay, so what the initiator would do is call RPC with some target process ID, as well as the function that should be run on that process, and then any arguments that we want to provide to that function. So these get packaged up in a message to be sent asynchronously to the target. And then at some later point, the function will execute on the target, and we'll get a reply back. So the initiation itself, it returns a future object. And what that future object, the value that it represents depends on the return type of the function. So if the function were returning an int, for instance, we'd get back a future event. If the RPC has a void return type, then it would just be an empty future. When the RPC actually runs on the target, after it completes, the target will send back a notification to the initiator that the RPC has completed, along with any return value. And so that would be, once that reply comes back to the initiator, at some point that feature will be readied, and the initiator can read the result or check for completion. And again, because this is asynchronous, we can have many of these RPCs active simultaneously, which allows us to hide the latency of doing the transfer and executing on some other process. Are there questions on these main features? So again, feel free to either put into Zoom chat or ask questions over Slack. And I will, this is my heads up that this is the extent of the review that we're doing today. All right, moving forward. In terms of compiling and running a UPC++ program, again, UPC++ is a library, but we still try to make it kind of as similar as possible to what you would get if you say you were doing Chapel or Coarray Fortran. So we have a compiler wrapper that wraps the underlying C++ compiler, GCC, Clang, Intel, or whatever you're using. And it takes similar arguments as the C++ compiler does. So in this case over here, for instance, we're compiling in debug mode the hello world.cpp program, and we're producing the hello world.exe executable. Then we also have a launch wrapper, and so this sort of abstracts over platform-specific tools for launching jobs, and that's UPCXX run. And so we can specify the number of nodes, the number of processes, and then the executable to run. Go ahead, Michelle.
There's a great question in Zoom chat. Alfred Tang is asking, by asynchronous, do you mean that there is no or little message passing?
Thanks, Michelle. So one of the things that we talked about yesterday is that all the models in this tutorial are one-sided. So we're not doing message passing. So with message passing, we need coordination between the initiator and the target to do a transfer. With one-sided communication, we don't need that coordination. So essentially, if we do an RMA, for instance, the initiator provides all the metadata, and then on most platforms, the network interface directly can place the data in the target memory location. So we're not doing message passing, but in terms of what we mean by asynchronous, really that means that the initiation and the completion are separate things. So we can initiate an operation and do other things while that while the communication is happening, and then later wait for the communication to complete. Okay, so again, what I mean by that is that we're not, by synchronous, it would be we'd have to wait for the entire thing to complete before moving forward to something else. And so I'll also point out, if you're familiar with MPI also has asynchrony in the form of I send, I receive. So it's sort of orthogonal to whether or not we're using message passing. All right, thanks for the question. So what happens when one processor needs a result from other processors to proceed? Well, this is something that we're not going to have time to get into any detail in this tutorial, but UPC++ actually has a well-defined progress model. And so, that's something that in most cases, programmers don't have to really worry about it. Things sort of proceed as you would expect. But if you were to do something like being inattentive for a long time, like maybe you do a long-running BLOS call or something like that, then that's the point at which you might need to pay attention to whether or not progress is being made. I see another question about whether UPC-XX run works with PBS. I'm going to defer to Paul and Dan on that one. Paul.
Very sorry, too many things going on here. I couldn't find my button to unmute. So we have integration with Slurm, PBS, LSF, the LSF version that IBM now resells. I honestly can't remember the name correctly, what's used on Summit. Usually there's some customization required per site, and we're definitely available to provide the tech support for the customization. Even just running on the Perlmutter and Frontier systems, which are both Slurm based, both of them are HP Cray EX systems, require a few different things to get well. And this is stuff that MPIs usually, when they're installed by the vendor or the center, they get tuned, but we're available. The short answer is yes. Longer answer is you might need our help, but we're very willing and able to provide it.
Thank you, Paul. And, while we're discussing this, I'll give you the link for site information, at least for ALCF, NERSC, and OLCF. And so you'll see instructions for the main machines at each of these sites. And, also kind of remind everyone that you can also install UPC++ on your own machine. And so that's really useful for development. You can develop on your own machine and then, make sure it runs on your own machine, and then hopefully it also works on clusters and supercomputers as well. Now, for the purposes of this tutorial, you just need the main tutorial link to get everything that you need for running. But afterwards, if you want to see, how do I run on some other machine, then this upcx.lbl.gov/site link has that information. All right, so let's actually take a look at an example in the tutorial materials, which is. Oh, yeah, go ahead.
I'm sorry. There was a question on Slack that I missed. I think it's a good question that everybody might be interested in. They're asking, is the future that you're talking about a UPC++ specific future type or a standard future?
It's an excellent question.
Yeah.
Yeah, thank you for bringing that up, Michelle. It's a UPC++X specific. So if you're familiar with standard C++ features, they actually serve a bit of a different purpose than UPC++ features. They both involve asynchrony, but in C++, they're also used for like concurrent access. Like you can have different threads work with the same feature, and that's for performance reasons, we didn't want to make that the same decision in UPC++. So in UPC++, we wanted the implementation of a feature to be as minimal overhead as possible. So in UPC++, they're primarily done for managing asynchrony rather than, say, directly communicating between threads or processes. But, the nice thing about C++ is that it has namespaces, and so we can have, std : future as a separate thing from UPC-XX : future. All right, great question. So let's go ahead and move forward to running the hello world example. So hopefully everyone is making progress or has already been set up. And so the tarball gives you, once you unpack it, gives you the cuff23 directory. You want to enter that and then enter the UPC XX subdirectory as well. And then from there, what you can do is you can make and do a make target to compile and run the programs that are there. Okay, so in this example here, we want to compile and run the hello world example. So we do make run dash hello world. And so let me switch over to a terminal so I can demonstrate. Sorry, just give me a second. All right. Okay, so I do a PWD to see that I am actually in the right directory. And then I can do an ls to see what files are there. And so the examples here are all the CPP files. And again, if we want to run a particular one, say if we want to run the Heat2D example, we just do make run dash and then put the name of the file minus the CPP extension. And so this will compile and then run it with default arguments. Okay. And then we can do the same thing with hello world. We see that there is a hello world.cpp program. And so we can do make run hello world to compile and run that. All right, if you want to run it with different arguments, different number of processes, what you should do is copy this UPCXX run command and change whatever you want to change. And so for instance, if we want to run on 8 processes instead, I would change that 4 to an 8. And then now we see output from 8 processes instead of from 4. All right, so I'm going to switch back to the slides. Okay. So I'm not going to repeat these overall instructions. Hopefully everyone has the main tutorial site handy somewhere. So if you want a refresher on the instructions, they're on that site. But what I'll do for subsequent examples is on the top right, I have the command for that particular example. So in this case, this is the hello world example. So taking a closer look at the code itself, here we have the full program, including this standard C++ boilerplate that we need. So we're going to be doing some I/O. So we pound include the standard I/O stream library. And then we also need to pound include the UPC++ library as well. And here we have our main function. The first thing that we do, because UPC++ is a library, we need to initialize it before we do anything else. Same thing with MPI. Once we do that initialization, then we can use UPC++ functions and objects. So in this case, we're just printing out from each process their process ID, which is what this rank me function returns. And then also this rank in the function returns the total number of processes. And by the way, just a clarification, we'll mostly use process and rank interchangeably in this presentation. If you're curious, kind of the difference is sort of a process ID is kind of a global property, whereas rank is relative to a team. So in this case, we're using the world team that includes all the processes. And so, apologies. So in this case, we're using, we're invoking these functions on the default world team. And so we're getting rank numbers that correspond to the process numbers. Now you'll see that this code, one other thing I'll point out is that just as a convention in these slides, I've put UPC++ operations in a red color and underlined. just to make it clear that this is what something that UPC++ provides. All right, so here we don't have any synchronization, so we don't get any. Again, a reminder that in the one-sided model, if you want synchronization, you have to ask for it. On the flip side, we don't pay for unnecessary synchronization. Okay, so in terms of the output, it can appear in any order, and in fact, on some platforms, it might even be interleaved. And then at the end, as with the MPI, we finalize the library as when we're done using it. Go ahead, Michelle.
Yeah, over in Slack, Joel Helmers is asking, does UPC-XX have a library function method to show the host name that the process is running on?
It's a good question. I don't recall one. Paul or Dan, do you remember?
I think you're asking about an
specific
equivalent to MPI. I can't remember what it was called, processor name or something like that. No, I don't believe we have anything directly of that nature.
So
there are a number of ways to get it, though.
Includes all of the POSIX environment. So get host name, which is a C POSIX call, is probably the right thing to use. UPC++ includes all of the POSIX standard on most systems and all of the standard C++ libraries. So all of those tools are also part of your toolbox at UPC++.
All right, thank you both. So, just to reiterate, you can get that information from reading environment variables, which because UPC++ is just a C++ library, you can use C++ mechanisms to do that, or POSIX specific mechanisms to do that. All right, thank you again for the question. So again, I want to reiterate that here, we don't have any synchronization, so we don't get it. Let's take a look at an alternate version of Hello World that does actually have synchronization. And so here what we're actually doing is we're iterating over all the processes, and in iteration I, process I will be printing. Okay, so we have a loop over the process IDs, and then we have a conditional that if the current iteration matches my process ID, then we'll do the printing. Now we're also additionally doing an RPC to process 0, so that all the prints happen from the same process. Otherwise we might have issues with different processes writing to standard out at the same time. Okay, so here we're essentially having process 0 do all the prints, and process 0 is only going to run one RPC at a time, so we're not going to get any overleaving. As far as what we're sending over to process 0 to execute, here we have an anonymous function or a lambda function. If you're unfamiliar with those, it's essentially allows us to put a function directly as an expression in the code itself. The syntax is similar to a normal function. The differences are that we don't have a return type, because that in general that gets inferred directly from the body. We don't have a name. We have this set of square brackets, which is something called the capture list. And that's something that we'll make use of later. And then we have the parameters for the function and the body. And so in this case, our lambda function is just doing a printout. But what it's actually printing, aside from the normal hello from process, is the rank of the initiator. And so that's taken as an argument in this function, and we actually provide it as an argument when we launch the RPC. Okay, so the initiator will send its rank number along with this this lambda to be executed on process 0. As we talked about before, this RPC will actually give us back a future. In this case, we want it to actually be synchronous because we don't want anybody else's print to happen before ours. Okay, before this iteration is complete. So we immediately wait on it. And then we have a barrier that prevents anyone from proceeding past it until everyone has reached it. Okay, so process I is not going to get past this wait until the RPC is executed. So that way we know that the printout has happened. And so this will prevent anyone else from moving on to the next iteration until that has completed. So if we actually run this on your own, hopefully you'll see that we'll always get the printouts happening in the ordered by process ID. So again, just to reiterate here, we wanted the synchronization, so we put it in. In the general case, if we wanted asynchrony, then we wouldn't immediately wait. We would get the future that RPC returns and then do something to overlap with it and potentially wait later. Yeah, go ahead, Michelle.
Yeah, I have another question from Slack. So from Shore, should we use keyword UPC XX : always to use any functions from the library, such as rank_n?
All right, great question. So in C++ terms, this is what's called a namespace. And so you have a couple of options here. If you want, you can use the namespace prefix. So this is called a qualified name to access something that lives inside that namespace. But you also have the option of putting in a using declaration in your code so that you don't need to do this. And there you also have a couple of options. For instance, if I just wanted to use barrier without the UPC XX qualification, then I could put in my code using UPC XX : barrier, and then later just say barrier. If I wanted everything that lives in the UPC XX namespace without qualification, then you can do using namespace UPC XX. And so just to give you an example what that looks like, in the previous Hello World example, we did that for the standard namespace. So we had this using namespace STD, which allowed us to use cout and endl, which actually live in the std namespace without that qualification.
All right, I do have another one.
Sure.
Yeah, that was a great answer to that one. So from Stephen Vormwald, where is the RPC call executed? In the main thread when it enters some UPC XX routine, a separate handler thread, not defined. It seems like on Slack, Stephen's figured this out, but I think this is a good question for everybody.
Yeah, it's a great question. So, one of the secret things that happens while you're waiting is that you're going to be essentially sitting there, and if an RPC comes in, or if you have something queued up on that process, it's going to run. And so that includes both the wait call over here, but also the barrier call over here, which again involves a wait inside of it. So in each iteration, after the first one, process 0 is going to be sitting here in the barrier, while somebody else does an RPC over to process 0. And as part of that wait at the barrier, it's going to see that RPC come in and execute it. So it is in the main thread. And again, the exact details are part of the progress model that I mentioned earlier. All right, so I do see a question on Zoom about the presentations. Are they posted already? So if you go to the main tutorial website, you'll see the presentations for yesterday, and at least my set of slides. I don't know if the Coarray Fortran ones have been posted yet, but they will be if they're not there already.
So there's a follow-up question about the RPC call one from Brad Richardson in Slack. Where does the argument to the RPC come from?
Yeah, so that's actually provided as part of the RPC call itself. So here, if we look at the arguments to the RPC call, we have the target process ID, we have the function object to be executed, and then we have any arguments to that function. And so in this case here, the initiator provided its own rank as the argument to that function.
I have
All right,
one
so
more.
yeah, go ahead.
There's lots of questions in Slack, so I'm just going to keep asking them. Andrea Huang is asking, how much will waiting for the RPC to complete slow down the program, if at all?
You know, if in this case we have something that's potentially executing on a different process, which means there's communication involved. We have to wait for that other process to see it and run it, and then send a response. So, you know, doing this immediate wait can be potentially expensive. And so in the general case, we want to try to overlap something else with this. And, you know, that's a nice segue to just going to actually just talk about that. So if we separate out that wait from the initiation, again, we get back a future object. And in the ideal case, we have something else to do in between that initiation and that wait. So I sort of mentioned this already, but I'll reiterate that in this case, we have a function object that doesn't have a return value. And so therefore, the feature that we get back doesn't have a value that it represents. It actually just represents whether or not the RPC is completed. And in C++ syntax terms, we have this feature as a template, and it happens to have no arguments in this case. But we still have angle brackets because it's a template. All right, more on a feature. So again, in general, we have a feature represents some values, which can be no values at all, as we just saw, or it can be one value, which is pretty common. But it can also be multiple values as well, and we'll actually see an example of that later today. So we have some set of values that the feature represents, and then also there's a ready state. You know, are those values ready, or has the underlying operation completed or not? So the feature itself essentially is a proxy for this data. And so you know, it's not the data itself. You can think of it as kind of similar to like a pointer to that data, an indirect reference to it. And then you know, when we call wait, we get back the data as part of that, but we can also obtain that data again if we wanted to using different calls. So waiting on a feature is one way to obtain the underlying data that the feature represents, but there's other things that we can do with the feature instead. So one of the main ones that we'll talk about a little bit later is that we can attach a callback to the feature that makes use of the values that the feature encapsulates. Okay, so again, rather than waiting on this feature and then using the underlying integer result, what we can do is we can instead attach another function object to this feature that will run when the feature is ready, and it will take as an argument that integer value. And again, we'll see more details about this later. All right, just as an example of doing some overlap, here I have a bit of an artificial example just to kind of demonstrate one way of making use of asynchrony. Okay, so here we have some code. Let's assume that this is just running on a single process, maybe process 0. Okay, and what process 0 wants to do is it wants to run some code on each of the other processes. Here I'm just doing, return its rank, but in general, we probably want to do something more meaningful. Okay, so we're looping over the process IDs and launching these RPCs, but not waiting on them yet. Okay, so instead, we'll store that feature inside a standard library vector. And then after we've launched all the RPCs, which allows them to actually get communicated concurrently and asynchronously, and potentially execute concurrently as well. Once we've done that, all the initiations, then we can go ahead and loop through each of the features and wait on them, just to ensure that they've completed. So again, this is an example of overlapping different RPCs with each other. There's other ways of, by the way, of waiting on groups of asynchronous operations, and we'll see one of those later today. Right. Other questions at this point?
I think we're good.
All right. Thank you, Michelle. So I'm going to transition to hopefully a more interesting example. So the example that I'll be using is similar to the 2D heat diffusion that we talked about yesterday, but slightly simplified. So essentially a one-dimensional version of this, just to make it a bit simpler to talk about. Later on, by the way, I will come back to the 2D heat diffusion and we'll take a look at underneath the hood to see how that's working. Okay, but the example we'll use first is this 1D version. It's an iterative algorithm that uses 2 copies of a grid, and we're in each time step we're computing new values for the grid points. Again, this is the same as what happens in the 2D heat diffusion. So in this example over here, I have 12 elements total, which I've distributed amongst 3 processes. And so process 0 owns elements 1 through 4. And process 1 owns elements 5 through 8, and process 2 owns the 9th through 12th elements. Okay. Now, in the tutorial examples, you'll see a jack1d .cpp file, and so this has many different variations of this algorithm. We'll cover some of the variations today. We won't cover all of them, but if you want to run them, again, it's the make run -jack1d command. If you want to take a look at the code, open up the jack1d.cpp file in an editor. Okay, and because we have different variants in terms of the data allocation, we end up in each process in its grid, it has space for something called the ghost cell, which is essentially space for the data that it needs from its neighbor to compute its boundary value. Okay, so if we look at the computation itself, to compute the new value at index I, we need the old values at index I -1, index I, and index I +1. Okay, so if I'm on process 1 and I need to compute the new value for the 5th element over here, I need the old value of element 5, element 6, but also element 4, which lives on process 0. And so one of the things that we'll talk about is different ways of doing that communication and obtaining that data. Okay, but as far as the grid layout itself, all of the variants have a space, for a copy of that element in the actual grid for each process. One more thing I want to point out, it's a small difference between the 2D heat diffusion and the 1D example that we're looking at here, is that in the 2D heat diffusion, we had fixed boundary conditions. In this 1D version, we actually have a circular boundary. So essentially, process 0's neighbor to the left is process 2. So to compute the new value for element 1, it actually uses the old value for element 12, and then vice versa. Okay, so again, this is a small difference between the 1D and 2D codes that we'll be looking at today. So here we have the computation, and again, because this is distributed, one of the things that we have to deal with is how do we actually communicate those boundary values? And so we'll look at a few different versions of how to do this and explore UPC++ features while we're doing it. Are there questions on the sort of high level computation itself?
Looks like we're good. And in about, just to let you know, in about 4 minutes, you're going to be halfway through at the halfway point.
Thank you, Michelle. All right, so let's, since we've been looking at RPC, let's actually start with an RPC-based boundary exchange. If we're doing an RPC, we need a function. We could write this as a lambda function. But I've actually written this here as a separate standalone function. Okay, so this is the get cell function, which takes an index and then just reads the value out of a global variable. So this old grid and new grid global variables are pointers to the start of the grids on the local process. And so if I'm process 1, what I need from process 0, I'm sorry, this is the right-hand side. So let's look at the right-hand side of this. So what I need from process 2 is I need the value of element 9 over here, which happens to be at index 1 into its array. For those of you who are familiar with Fortran, by the way, indexing in C++ starts at 0. So this would be index 0, this would be index 1. Okay, so again, what I need is that the value of element 9. So I'm going to send an RPC to my right neighbor, asking it to run this get cell function with the index 1 as the argument. And so what I get back from that is a future with a double underlying it. And here I've just synchronously called wait. But when we look at the full code, we'll actually make this asynchronous with some overlap. And one thing that I'll mention here, we talked about the UPC-XX qualifier. From here on out, I'm actually going to elide it just to make it the code easier to read. So again, think of this as I did using namespace UPC-XX at the top. All right, so let's look at the full code for our time step. Again, we're going to be using this RPC of this get cell function to obtain the data we need from our neighbor. But we want to take advantage of asynchrony. We want to overlap as much as we can. So at the beginning of the time step, what we'll do is we'll actually launch the RPCs over to our neighbors to obtain the data that we need. And we get back these future of doubles. And then we can overlap that with interior computation. So here I'm computing the new interior values where I have all the data that I need. So for element 6 and 7, it just uses the old values of elements 5 through 8. So I don't need the old values of elements 4 through 9 to do that computation. So after I'm done with the interior computation, that's the point where I can now wait on those features and wait for that communication to complete in order to now compute the new values for the boundary elements. Okay, so here for computing the new value for this element over here, I use the feature that I sent over to my left neighbor to get the old value of element 4. And here I've done the same with my right neighbor. There are questions on this code, what this code is doing.
And people can raise their hand if they'd like to potentially come off mute and ask the question themselves. Or you can put something in Slack, or you can put something in the Zoom chat.
Yeah, absolutely. Thank you for the reminder. And Dan mentions in the chat that this is in the Jacobi RPC function, Jacobi _ RPC function in the jack1d.cpp file in the tutorial examples. Thank you, Dan. All right, so again, what this illustrates is that we can take advantage of asynchrony by overlapping our communication of the boundary cells with interior computation, and also overlapping those two communications with each other. And you know, aside from the weights here, we don't have any synchronization, and you know, we'll see in a second that that's actually a problem because we're going to end up swapping our grids for use in the next iteration. Okay, so again, we have an iterative algorithm that's computing new values for each of these grid elements. But rather than allocating new grids in every single iteration, the way we do this is we just go back and forth between two copies of the grid. Okay, so once we've computed all the new values in this iteration, then that new grid becomes our old grid for the next iteration, and we reuse our previous old grid as the new grid. And in C++, we can accomplish this rather simply by just swapping the pointers using the standard swap function here. So I see a question about RPC knows the current rank. You see left and right. And so, you know, if you actually look at the code, we compute our left and right neighbors, what their process IDs are once, because that never changes in this particular algorithm. And so you can imagine that, you know, there's just variables that have the process IDs of our left and right neighbor. Okay, and we're just reusing that rather than computing it every single time. All right, so this swap over here, we're actually modifying what old grid and new grid are pointing to. But the RPCs themselves also use old grid. So going back to the definition of git cell over here, which is what the RPC is running, we see it actually does a read on old grid. And so now we have to be careful in terms of, you know, when does this RPC happen where it's actually reading old grid? And when does the swap happen where it's actually modifying old grid to, you know, point at something else? Okay, so this is actually something called a race condition, which is when you have multiple threads or processes accessing the same piece of data, where at least one of them is modifying it. And here we have the swap is modifying that old grid. So this is indeed a problem. Okay. So in the context of this particular example, what can potentially happen is that we can have one process send an RPC over to another process to read its old grid. But that other process could have moved on to some other, the next iteration. And so it might have a different value for old grid than what the initiator was expecting. Okay. And so we have, this is something that, you know, we need to be very careful of when we're doing one-sided communication. Because again, one-sided communication decouples communication or data movement from the synchronization. And the plus side of that is that, we don't pay for unnecessary synchronization. The trade-off is that if we need synchronization, we have to ask for it. So a question in the meeting chat about which file. So this jack1d.cpp, jac1d.cpp. Okay, so there's many different ways of providing the synchronization, including doing point-to-point synchronization. We'll just for this tutorial today, we'll just stick to the simple version, which is using barriers, since hopefully we've already seen what barriers are, and so hopefully we know what they're doing. Okay. So in this case here, we're going to insert two barriers. The first barrier over here ensures that all the RPCs have completed before the swap happens. And then the second barrier ensures that the swap happens before the RPCs in the next iteration run. And so again, if you take a look at the Jacobi RPC function in the jack1d.cpp file, you'll see that it's doing exactly this. And again, I'll just reiterate the high level point, which is in the one-sided model, we get synchronization when we ask for it. And in this case, we needed synchronization, so we had to ask for it. All right, so, this, hopefully we've taken a look at the RPC version of the boundary exchange. As I mentioned previously, there's other ways to do the boundary exchange. So for the next one, let's take a look at using RMA instead. And so before we actually take a look at the boundary exchange itself, let me just briefly explain what RMA primitives are there in UPC++. We saw an example of rget beforehand, which is a get from a potentially remote location. And so what it takes as an argument is a global pointer, which can be potentially referring to some data on a different process. And again, this does a one-sided get, but it's asynchronous, so we get back a future. This version here is what we refer to as scalar, which is we're just reading a single data value. And in that case, for the get, the data value itself is just encapsulated in the future. And so here since we have a global pointer of int, we're reading an int value, and so we get back a future of int. Now we also have puts. The scalar version, we specify the actual data value that we want to send over to some remote, potentially remote location directly as part of the rput call. Okay, so we provide the rput, the data value, and then the global pointer where we want that data value to be placed. And here we're not getting back a value as a result, but what we get back is a future that represents whether or not that put has completed. Okay, so if at some later point in time we want to make sure the put has completed, then we can wait on that future to be certain of that. All right, so again, the scalar versions are doing a get or a put of a single data value. We also have vector versions that allow us to do gets and puts on not just a single value, but like an array of values. And in that case, what we need to specify is we need to specify the source memory, the target memory, and then the number of elements that we want to transfer. In the case of our get, our remote is going to be a global pointer, or sorry, our source is going to be a global pointer, and then our destination is going to be a local pointer. In the case of our put, it's the other way around. We have a local source and we have a remote destination. And in both cases, what we get back is a future just representing whether or not that communication is completed. The future itself doesn't encapsulate the values because, they're going to be written directly into the target memory that we provided. Now, for completeness, I'll mention that we also have a copy operation in UPC++ that allows us to do like a third-party remote-to-remote transfer. But for the purposes of today, we're going to be sticking to just the simpler gets and puts. All right, so let's take a look at how we might use them to do the boundary exchange in the 1D Jacobi algorithm. And so this is where we're going to actually be make use of the ghost cells that we allocated in our grids. Okay, so those ghost cells are actually going to be the destination of our transfers. So again, if we're on process 1, we might have a global pointer that's pointing to the beginning of the grid on process 0. And so what we can do is we can do an arget to obtain the element that we want from that process. Okay, and if we do the math right, the element that we want is actually this element 4 here, which is at position n-2 in the array, if n is the size of the array. Okay, so I've done that here. An arget, again, we just provide the source memory, which in this case is actually located on our left neighbor. We do some fancy C++ pointer arithmetic to actually adjust the pointer to be pointing at the value that we want, the element that we want. And on this slide, I've just done an immediate wait. Of course, we really want to overlap, and so we will be overlapping later. And thanks again, Dan, for pointing out that the RMA example is the Jacobi _ arget function in the jack1d.cpp file. Okay, so these are one-sided communication. Again, we don't have a send and receive like you would in two-sided message passing. One of the things that we do need is in UPC++, for us to be able to do this, these grids need to be allocated in shared memory. Okay, so one of the things that we talked about yesterday and didn't get a chance to review today, but hopefully I'll review verbally, is that in UPC++, each process has a private segment and it has a shared segment. And the global address space is comprised of the union of those shared segments. And so to give another process access to our grid, that grid needs to be allocated in the shared segment. All right, so let's take a look at how to do that allocation. If we do a standard C++ allocation using new, then that gives us something in private memory. To get something in shared memory, we need to use a UPC++ allocation function. And so in this case, since our grids are represented as arrays, we use the new array function template that UPC++ provides to do that allocation. Okay, so it's parameterized by the element type. In this case, we have doubles as the element type, and then we give it the size, the number of elements that we want. So this does an allocation in shared memory, and it gives us back a global pointer that's referencing that newly allocated memory. Now, in this case, the global pointer happens to be pointing to something on the same process. But again, it is something that is located in the shared segment of that process. So a couple things I want to mention about the specifics of this allocation. These aren't collective calls. Each process allocates its own memory. So each process individually does these allocations. There isn't any synchronization here. Now, we may need some synchronization if we were, say, using RPC to obtain this from a different process. We might need some synchronization to ensure that it's been allocated. But what we'll actually see later is we'll see a better way of doing this, of obtaining these pointers from our neighbors. So I'm going to defer that for now. For now, again, I just want to mention that we need to allocate the grids in shared memory. And then as far as using them on the same process, generally speaking, we don't want to be doing accesses through a global pointer, because that typically involves a conditional to check, where that memory is located. And instead, since we know that these were, we did the allocation of this memory, we own that memory, we can just convert it into a normal C++ pointer. So there's a local function, a local method on a global pointer that does that conversion. And so here I have old grid and new grid as just normal C++ pointers, and I convert the global pointers to them, and so then the computation can just be done through the normal C++ pointers. Are there questions about the storage allocation?
I'm not seeing any, but anybody who wants to ask, feel free to raise your hand or ask in Slack. Go ahead and keep going, Amr, and
All right.
I'll let you know when questions pop up.
All right, thank you. Okay, so if we actually take a look at the boundary exchange using RMAs. So as with the RPC version, we start off in each time step by initiating our one-sided transfers. And so here we have the argits to our neighbors. We do the overlapped computation on the interior cells, and then we can wait for the argits to complete before computing the boundary values. So again, this looks a lot like the organization for the RPC version. Now, as I mentioned previously, wait is one way we can sort of deal with dependent computation. Here we have some computation of the boundary that depends on the argits to have completed. But an alternative is to use then to attach a callback to do that. Okay, so what I'm showing here is the alternative where, once we launch the argit, we actually attach a callback to that resulting feature that encapsulates the computation that we want to do. Okay, and in this case over here, I'm doing the vector argit. So that argit returns an empty feature, a feature that doesn't hold a value. And so the lambda function here doesn't take in an argument. If the feature we have actually does encapsulate a value, then the function we provide needs to take in that value. And so in this case, I've used the scalar argit, which gives us back a feature of double. And then I've attached a callback that takes in that double value and then uses it directly. So again, I can attach this callback, and what this callback gives us back is another feature. Again, because this callback itself is asynchronous, it cannot run until the transfer is completed. And so because the callback itself runs asynchronously, we get back a feature that represents the result of that callback. And in both of these cases, our callback doesn't return a value, so we get back an empty feature. And so, I see a comment that wait and then sound like synchronous methods. So wait is, then is not. Okay, then is asynchronous. Essentially what it's saying is that when this feature becomes ready, when this arget has completed, then do this thing. Okay, but that could be at some later point. And so that's why we get back from this then call, we get back its own feature to represent whether or not that callback has run. Now, the example we see here is just a simple, we're doing a single communication and then we're attaching one callback to it. But the nice thing is that we can actually construct more complicated chains of callbacks and essentially a longer asynchronous computation. So for instance, we can have an arget, we can attach a callback that does some computation and it produces some other value. In this case, it produces a double value. We can attach another callback to that that consumes that value and in fact launches another asynchronous operation. And then what we get back is a feature that represents this entire chain of computation. And again, this it doesn't necessarily have run yet. It won't run until that initial arget is complete. So this whole thing is asynchronous. And we can do a single wait at the end to wait for the entire computation to ensure that the entire computation is completed. All right, so what we're seeing here is, again, a straight line chain of asynchronous work. We also can have directed acyclic graphs or DAGs using winall. Okay, so winall is something provided by the UPC++ library, which allows us to combine the results from multiple operations. So in this case over here, I've launched two argets, scalar one, so I get back futures that represent values. And then I can do a winall to combine them both into a single future that represents both values as well as the completion of both of those operations. And then I can attach something to that. And again, now I have a more complicated dependency graph. And I have the single feature that represents that in the entirety of that graph. And I can do a single wait on it to ensure that it has completed. All right, so we have another version of the Jacobi boundary exchange that makes use of winall. So the previous version that we saw did separate gets with separate features, and then we waited on them individually. Here, this version, first of all, we're using puts instead of gets, but rather than waiting on them individually, we combine them into a single feature using winall. We do the interior computation. We do a wait to ensure that our puts have completed. That this process's puts have completed. We have a barrier synchronization, which ensures that our incoming puts have completed. And so therefore we have the data that we need, and then we can go ahead and do the boundary computation. So I see a question about, should the type of feature 3 be future of future? It's a great question. The library collapses that into just a single feature. So, the reason, I think the reason why the question was asked is because our put returns a future, and then, does it then give us back a future of a future? No, it actually just gives us back a single level feature to represent that result. All right, so let's template magic. Yes, that's a wonderful thing in C++. So I'm going to briefly talk about the 2D heat diffusion. Again, it looks a lot like the 1D Jacobi that we've seen. So again, this is in heat2d.cpp. So we have our global problem domain. and we divide that up. In our implementation, we actually do a one-dimensional distribution of the 2D domain. And so then each process has its own local grids, representing its portion of the domain. Now, again, to do a boundary computation, we need data from our neighbors. For that communication to happen, unlike the 1D Jacobi where we use ghost cells, in the 2D heat diffusion, we actually use separate arrays that represent the landing zone for receiving data from our neighbor. Okay, so in the code, these are called T up and T down. And again, T up is where my upwards neighbor is going to put its data, where it's going to transfer its data, and then I can later on use that to compute my my boundary values. And then if we actually look at the code for our time step, it looks very much like the 1D example that we saw. We initiate our communication. And I'll point out that what I have on the slide is slightly simplified compared to what's in the code that we distributed, because I'm not accounting for, process 0 not having, a downward neighbor and process n-1 not having an upward neighbor. Okay, so there's a little bit more logic in the actual code that we gave you that accounts for that fact. But if a process has both neighbors, then it does two outputs to its neighbors, combines them with a win-all, does the overlap computation of the interior. Now, does the wait to ensure that the outgoing puts have completed, a barrier to ensure that the incoming puts have also completed, and then it can compute the boundary values and then do the swap and barrier to set up for the next time step. All right, so hopefully this gives you a sense of what at least the computation and boundary exchange portion of the 2D heat diffusion. There's one more piece I want to talk about, which has to do with the setup. Again, in order to do these, essentially, in order to do the puts, we need to have a global pointer to the landing zone on our neighbor. Okay, so how do we get that? UPC++ provides something called a distributed object that allows us to easily communicate these between processes. And so essentially, you can think of a distributed object as an object that's partitioned over a set of processes where each process has a piece of it. And in fact, in UPC++, this doesn't necessarily need to be over all the processes. It can actually be over a subset of the processes, which we refer to as a team. So in this example over here, I have a distributed object. The value that each process is going to have is an integer. And so it's parameterized by int. And in the constructor over here, I actually provide the value, which I'm just providing a random value on each process. Okay, and so what we have is amongst the processes, each process has an integer value that's underlying this just distributed object. This is similar to a Coarray, which you'll see in Damien's presentation later today. Go ahead, Michelle.
Well, this is not about this specific example, but there is a question in Slack asking a broader question about, what are some reasons one might use UPC++ instead of MPI?
So we talked a little bit about this yesterday. One reason is because UPC++ communication has lower overheads than MPI. So we actually showed you some performance numbers yesterday on that. But hopefully we'll get a chance to talk a little bit about some of the applications that have been written using UPC++. And they found that UPC++ provides lots of features that make it easier to write code compared to MPI. So I think the most obvious one is RPC, right? MPI doesn't have a concept of RPC, whereas UPC++ does.
Okay. And the other thing I wanted to mention is that there are 15 minutes left. And so we're probably going to try to answer the Slack and Zoom chat questions asynchronously for folks, so that you can get through the rest of your material, if that's okay with you.
All right, sounds good.
Mm-hmm.
Thank you. So again, going back to the 2D heat diffusion example, this illustrates how a distributed object can be used to communicate the global pointers. So the top here is just doing the storage allocation, which we already saw for the 1D example. We construct landing zones in shared memory, and then convert them to local pointers locally. And then we construct distributed objects over the global pointers. And so again, here we have two distributed objects where each process contributes a pointer to its landing zone for the neighbor in that direction. And then we can do a fetch on the distributed object from our neighbors for the global pointer to its grids. And here we've done this synchronously. We could do this asynchronously instead. Fetch gives us back a future, and so we could have overlapped if we wanted. But just for simplicity, we just immediately waited. Okay. And then the only synchronization we need is at the end, just to make sure that everyone has retrieved the pointers that they need before the distributed object gets destroyed. Okay. So again, this code is, you can see the details of it in the heat2d.cpp example, and it gives us a very simple way of doing this communication. All right, another thing that we can, another example that we can do with distributed objects is a distributed hash table, which is actually a data structure that's really important for the metagenomics application that hopefully I'll get a chance to talk about in a few minutes. And essentially what this is the distributed analog of std unordered map, which is a hash table in C++, or if you're familiar with Python, is dictionary. And so we have we associate keys with the values, and we want to be able to insert key value pairs into our table. We want to be able to look up the value associated with a key. And the way that we're going to do this is with a distributed object, where each individual piece on each process is just going to be a local standard library unordered map. And so, as far as the data itself, here I've introduced a type alias just to make, it's simpler to type. But essentially, again, our data representation is going to be a distributed object with an unordered map on each process. And the unordered map itself, in this example here, we're mapping, we're using the string type as the key and the value type. And so we create this distributed object initially with empty maps. And then in terms of actually hashing a key, what we do is we figure out who owns the partition. And the way we do that is we just compute the hash value for the key and then mod it by the number of processes. Okay, so that will tell us which partition of the hash table the key value pair should be located at. So let's just briefly look at one operation There's other operations in the code. And by the way, this is the DMAP insert test. If you're looking at the code that was distributed in the tutorial examples. But essentially what we have to do an insertion, we use an RPC, and it's actually pretty straightforward. So to insert a key value pair, what we do is we first figure out, okay, who owns the partition of the distributed hash table associated with that key. And so we call the getTargetRank function to obtain the ID of that process. And then we send over this Lambda function that actually does the insertion over at the owner. Okay. And the arguments it takes is the distributed object. RPC actually has specific logic for basically converting this over to the targets representative of this distributed object. So essentially, the RPC transfer converts this to a universal name. And then on the remote side, on the target, it converts it back to the target's partition of the distributed object. And so then we also provide, the key and value that we want to be inserting into the table. And then as far as the code that actually runs on the target, that just accesses the underlying unordered map. It's actually what the star operation does, is it on a distributed object, it actually gives us the underlying value, which in this case happens to be an unordered map. And then we just use standard C++ to insert into there. And of course, this RPC gives us back a future representing whether or not it is completed. All right, so the high level observation I want to make is that, the combination of a distributed object and RPC makes this code really simple. We just have, make use of the distributed object as an argument to our RPC, and the code that the RPC runs is, just doing the insertion locally using standard C++. All right, in the interest of time, I'm going to skip over the rest of the distributed hash table operations, but hopefully you get a chance to look at the code yourself and look at the slides offline to see that. And one of the things that you'll see is the other operations are essentially as simple as this one.
Yeah, Amr, you started about 5 minutes in, so can you wrap up in about 7 or 8 minutes at 10:35?
Sounds good.
Or 35 after?
Yeah, will do. So I'll briefly mention, what we've seen so far are kind of the basics of UPC++, using one-sided communication with RMA and using RPC to transfer computation. We've seen the basics of using asynchrony with futures and wait, and also, kind of the basics of storage management and communicating pointers between processes. UPC++ has a ton more features that are also extremely useful. We just don't have time to cover them all today. And so here I have a non-exhaustive list of things that the UPC++ library provides. So a couple of highlights. We have remote atomic operations that actually utilize the hardware capabilities of modern networks that can offload those atomic operations. There's a question yesterday about if we do an RPC, do all the data types need to be trivially copyable? The answer is no, because we actually have a serialization interface, and we actually provide serialization of many standard library types. And in fact, in the DHT example, we sent over a std string, and that's because we implement serialization of that type. There's additional forms of providing synchronization. So for instance, point-to-point synchronization using something called the signal input. We have non-contiguous RMAs that do automated packing and aggregation. And then we have direct transfer from GPU and CPU between GPU and CPU memory using hardware support for that. So at the end, I'll show you a slide that has link to more information that you can learn about all of these wonderful features that we have. But for the rest of my time today, I'd actually like to talk a little bit about some of the applications that have been written in UPC++. So there are a number that have been written. Some of them have involved collaborators from our own group at Berkeley Lab. Some of them have been done entirely by other folks. And so what we'll talk about is the first three over here, very briefly, which is we have SymPack, a sparse symmetric matrix solver. We have SymCove, which is a simulation of the COVID-19 infection in a model of lungs. And then we have meta-k-mer, which is a genomics application that is written in UPC++. And again, there are several other applications that have made extensive use of UPC++. So SymPack, I don't have time to go over the details. If you want the details, there's a link at the bottom, upcxx.lbl.gov/SymPack. But just kind of a brief summary of how it's implemented. It's implemented over UPC++, making extensive use of both remote procedure call as well as one-sided communication. And in fact, because UPC++ interoperates with MPI, so does the SymPack library. And in fact, you can use the library in an MPI application. And you know what we see from the implementation of SymPack is that by using UPC++, it actually provides better performance than state-of-the-art solvers. So on the right-hand side, I have an example of one particular matrix that's comparing PASTEAQs, which is a state-of-the-art sparse symmetric solver, with SymPack, with two different versions of SymPack. And you can see that essentially at all scales shown here, SymPack is faster by about a factor of 2 at the larger scales. And again, this is something that was enabled by UPC++ and UPC++ features like RPC. Another example that I mentioned, SymCove, which is modeling immune response to COVID-19 infection. And so this actually models the infection of the lungs with COVID-19, and specifically it's modeling T cells, the T cell response, as opposed to the antibody response. And so it's an agent-based model where you have many agents representing both T cells as well as viral particles. It's modeled over a very complex structure of representing the lungs, and it's running for many time steps. And again, like with SymPack, this makes extensive use of UPC++ features. It's a very irregular computation. Particles move over time. You'll have a higher load of particles in some areas of the lungs at one point in time compared to other points in time. And so it ends up being very, very irregular. And so the application itself, again, it makes extensive use of remote procedure call to manage this irregularity. It makes extensive use of the asynchrony to overlap communication and computation. And what the what the developers reported is that UPC++ allowed them to very easily develop the first prototype, very easily get good performance scaling to run this complicated simulation on supercomputers. Now, there's more detail at this link down here. And then, one of the things I want to mention is this actually enabled science to be done in real time during the pandemic. And in fact, the collaborators actually published in the PLOS Computational Biology Journal in December 2021, using results from this simulation. All right, so the last application that I want to talk about is MetaHitmer, which is part of the Exabiome project. And the goal here is something called metagenomics. So essentially, we want to learn something about the genomes that are present in some environmental sample, and maybe to answer some questions, some science question. For instance, what happens to microbes after a wildfire? And so MetaHitmer is, kind of was the first distributed implementation of this metagenomics assembly. And again, what we get is we get DNA samples from the environment. Those get sequenced into k-mers, and Michelle talked a lot about those yesterday. They need to be assembled into full genomes. And we end up with lots of data that really requires distributed computing to be able to do. Now, for instance, the wetlands data mentioned here is 2.6 terabytes, and that assembly took 3.5 hours on 16,000 cores in 2018. So more recently, the MetaHitmer, the Exabiome group keeps on breaking their own records in terms of how large of a assembly they can do. So last year they did a 30 terabyte assembly on OLCF Summit on 63,000 cores and 9,000 GPUs. So again, here we have UPC++ basically enabling new science to be done. And again, the UPC+, the MetaHitmer developers have reported that UPC++ has enabled them to write their code more simply and get significantly better performance than the previous MPI implementation. And more details are at this link over here. All right, I think I'm a minute over, so I'm going to end here with just a final slide with more resources. Now, sadly, we had limited time today. We couldn't talk about everything that UPC++ has to offer. And so if you go to upcxx.lbl.gov, you'll see a lot more details. And in particular, this training sublink has a lot more to get up and running in UPC++, including a full programmer's guide, as well as videos and exercises from past tutorials that have been longer and so have been more detailed than we were able to be today. And then I'll leave you with some testimonials from outside users of UPC++, who have really found it to be useful.
Thank you, Amr. All right, everyone. You could use your reactions to thank Amr for his excellent tutorial on UPC++. Keep putting those questions into Slack, and we'll keep answering. Actually, there is one question here in the Zoom. Do you see that?
Yeah, I do, and I'll answer it. But I'll mention, so we're officially in our break, so feel free to leave and come back in about 10 minutes. Yeah, we didn't really have time to talk about this during the main portion of the presentation, but essentially UPC++ supports direct GPU memory transfers between either local or remote CPUs and GPUs. And so, modern GPUs and network interfaces can actually do this direct transfer. So on the right-hand side, we see what that looks like. It's essentially, not needing to stage through host memory in order to do a transfer to, some remote location. Whereas without this support, you'd have to do a copy into host memory and then inject it into the network from host memory. And, just want to briefly show you why this is important. And so here we have performance results on OLCF Summit. The circles are GasNet. The closed circles are with the direct transfer support using things like NVIDIA GDR or AMD ROCm direct transfers, and the blue circles are without it. And for small transfers, we see over an order of magnitude of difference in terms of bandwidth, 30x, and even for larger transfers, we see a 2x difference in bandwidth. And then I'll also take this opportunity to plug GasNet because we also have an MPI comparison on this machine, MPI with the direct transfer support. So hopefully comparing apples to apples as best as we can. And we see that for smaller message sizes, GasNet actually does better, and it reaches saturation at smaller sizes than MPI does. So again, another reason to use GasNet and UPC++.
Welcome to day 2 of the Coarray Fortran portion of this tutorial. Lots to cover today. I want to start off by showing some examples of Coarray Fortran at scale. Something that might have been good to include on the first day. I got a little bit jealous seeing all the great applications with UPC++ and Chapel, so we'll show some success stories for Coarray Fortran today as well. And then we're going to cover several features that I would actually label as beginner features. Teams, image enumeration, things like this image, num images. We talked about some of these yesterday. Synchronization, collective subroutines. And what I think is interesting there is that in my anecdotal experience, that covers probably about 30 to 40% of scientific applications out there. And these are the applications that I think most people will refer to as embarrassingly parallel, where you need to launch a bunch of processes and then maybe compute some, you're doing maybe a parametric study and you want to compute some statistics across the different simulations that you just did. Those 4 that I just named are pretty much all you need, which makes it a little bit ironic that it's called Coarray Fortran, because it's not until you get to the more intermediate or advanced levels of programming that you actually need Coarrays. There are a lot of applications that don't. So then we'll talk about Coarrays, and finally, the most advanced feature we'll talk about is events. Let me also first step back. As we were wrapping up yesterday, I had one more slide that I'll just go over quickly as kind of a summary, a wrap up of things that we talked about yesterday. So you'll recall that the philosophy that inspired Bob Numrick when he developed Coarrays was trying to come up with the smallest addition to the language, which back then was Fortran 95, that would take the language parallel in a way that didn't require people to learn a lot of new things to do the parallel programming. And the basic idea that he came up with and then worked with John Reed to get into the standard is to add square brackets, which we call co-subscripts. So you have these data structures, and I'm showing a kind of silly example that's really just there so that I can show the various forms of syntax that I want. It's not really doing anything especially useful, but you can see where there's a declaration, the line that says type foo object local size, and the square brackets there tell you that that's a coarray. And one of the points I wanted to make in summary yesterday is that these features, for the most part, integrate nicely with other features in the language. So for example, if you're familiar with Fortran's colon notation, which I think was borrowed from MATLAB, you can see in the line that says if me is less than n, where I'm accessing 2 elements of the array, elements 1 through 2. And I can do that for something that is a coarray or for something that is not. So it integrates nicely with the array features in the language, and the fact that that is an object and not just something of intrinsic type says it's also integrating to some extent with the object-oriented features. We'll probably at one point today get a chance to talk a little bit about at least one object-oriented feature that isn't quite there yet, which is sharing, or I guess communicating polymorphic objects. But there's a brand new idea that my colleague Brad Richardson just came up with that might save the day on how to do that, even though the language doesn't really give you obvious support for it. And this feature set is minimally invasive. That same line that says if me is less than n, on the left side, I drop the square brackets because I know that I just want to assign to local data. And this is especially important if you ever have the experience of parallelizing a legacy Fortran code, a serial code. When you know you want to distribute data, you change your declaration. That's why we have the square brackets in the declaration. When you know you want to communicate, you use the square brackets, and lots of code actually can stay the same. You can even pass the local portion of a coarray into a procedure that was written strictly as a serial procedure, and that procedure has no idea that it's receiving, a part of a distributed object. So that's a nice thing for parallelizing legacy codes. And also importantly, communication is explicit. So you know that if you see square brackets, communication can happen unless the value inside the square brackets is telling you that you're just working with the image that's executing the line. But otherwise, you know that communication can happen when you see square brackets, and you know that if there are no square brackets, there's no communication going on. Okay, a few examples of Coarray Fortran at scale. And some of these go pretty far back because the idea of Coarrays goes back to the late 90s. This is a paper from 2011, published by several people at Berkeley Lab, as also at Cray at the time. And they were looking at a multi-threaded magnetic fusion application. And specifically, they focused in on what was then the bottleneck in the code, which was the shifting of charged particles in simulating a tokamak, which I think is Russian for toroidal chamber machine. So any of you who are familiar with magnetic fusion have probably seen the kind of plot that you see on the left showing this donut-shaped device, and they're simulating the motion of the particles around the torus. And so they wanted to compare Coarray Fortran with OpenMPI and also two-sided MPI that also had OpenMP, and they wanted to compare those two cases. And they ran experiments on up to 130,000 processors and saw a speed up of 58% relative to even the best multi-threaded MPI algorithm for the same part of the code. One of the things that's really important too is that they looked at doing one-sided communication, and they said the complexity requirement was just prohibitive. It is important, however, to know that the one-sided features came into MPI and MPI2, and apparently those were, I'm not an MPI programmer and certainly wasn't paying attention when that was happening, but my understanding is that those features were improved in MPI3, and so there is better support with MPI3 for one-sided communication, but it is still very challenging to write. And so again, anecdotally, I would say that probably 90% of scientific codes that I encounter are using two-sided MPI. And so it's important to note that you've heard a lot so far yesterday and today about the simplicity of the PGAS languages. It's also important to note that you can get great performance. You can, in fact, get better performance. So you don't necessarily have to trade off programmability for performance. You can get both. This is from 2015. One of the co-authors is John Reed. He was, for several years, the convener of the Fortran, the worldwide WG5 Fortran committee, and he's still active on the committee. And in this paper, they looked at 3 different applications, magnetohydrodynamics, so that's actually very similar to what we just saw with the plasma fusion problem. They also looked at 3D FFTs, a problem that's close to my heart. Most of my early work, my dissertation and several papers thereafter were using spectral methods, which are infinite order accurate methods. They converge faster than any power of your grid spacing. And they also looked at multi-grid methods, specifically with pointwise smoothers. And I think that's a relevant one for the tutorial today, because the heat equation can be thought of as a smoothing equation. Basically, what you're doing is smoothing out temperatures over time. And they compared Coarray Fortran. Now, this study was a few years later than the previous one, so they did look at the MPI3 one-sided features. And so now, when you switch to one-sided MPI3, first of all, as I said, your complexity has gone up considerably in terms of writing the code. At least until fairly recently, most of the people I had talked to who had looked at most people I talked to about one-sided communication who were domain scientists, not computer scientists, fell into one of three categories. Either they hadn't heard of it, or they looked at it and ran away screaming, or they tried it and couldn't get it to work. And I've only run into a few exceptions to those three categories. So now you do get comparable performance, but with a lot greater complexity. And so they did simulations up to 65,000 cores, and they found that Coarray Fortran draws level with MPI3 or shows a slight advantage, and considerable advantage over, in this case, they're saying MPI2, and what they mean is two-sided MPI. And of course, they note that the CAF code is much easier to write. So you can see on the left there, they're comparing Coarray Fortran with MPI3, and pretty even across the problem sizes that they were looking at in this particular graph. Some cases MPI is a little bit faster, some cases Coarray Fortran is faster, but about the same if you're writing MPI3 one-sided. This is Coarray Fortran's use in a weather model from the European Center for Medium Range Weather Forecast, ECMWF. And so this is their operational weather forecast model. If you're looking at a forecast, you're probably seeing results of this code if it's coming from Europe. And they compared Coarray Fortran to two-sided MPI. This is the comparison that I like to make because it's comparing apples to apples in the sense of practice. It's in the sense of what's actually used in scientific codes. So highlights of this one, they did simulations on more than 60,000 cores. They saw an improvement from using Coarray Fortran over using MPI. And by the way, the main reason you're seeing all these comparisons to MPI is because MPI is the dominant paradigm. I've seen data, for example, for NERSC that over 90% of codes are using MPI. So they saw improvements that peaked around 40,000 cores at about 21% improvement. And then there is a dip after that, but they did some investigation and realized that the dip wasn't that the Coarray Fortran was, somehow not scaling well as they went to more cores. It was just that the MPI was starting to catch up. Basically, it was doing better. And lastly, this was a study that I was part of with my collaborators, Soren Rasmussen, Ethan Gutman. They're both at NCAR now, National Center for Atmospheric Research, and Brian Friesen, who's here at NERSC, Salvatore Filippone, who's at the University of Rome, Tor Vergata, and Irene Melitsas, who's at Cranfield University. And we were looking at ICAR, the model that I mentioned yesterday. And ICAR essentially models the regional impacts of global climate change. So it takes output from a global circulation model and uses that as input to a much finer scale regional model. And the goal is that the person who wrote this, Ethan Gutman, is a hydrologist. The goal is to get better predictions of precipitation, because that gives the hydrologist who's interested in surface waters, groundwater, and estuaries and things like that, that gives them better information for their hydrology models. So in this paper, we looked at Coarray Fortran building on top of one-sided MPI, but also Coarray Fortran building on top of OpenSHMEM. This is one of my favorite stories from my career, because I was standing in the hallway at NCAR talking to Ethan, and we were complaining about some problems we were having with the SGI, Silicon Graphics company at the time, implementation of MPI, which was still fairly immature. Even the developer from SGI at the time, who came to give a talk at NCAR, recommended against using the one-sided features in the SGI MPI. And Alessandro Fanfarillo, who was the original developer on OpenCoalRace, walked by and said, well, have you tried OpenSHMEM? And I didn't even at the time know that OpenSHMEM was an option. And he said, oh, well, I've written an OpenSHMEM layer, for OpenCoalRace, which we were using with G-Fortran. And as I mentioned yesterday, at that point, it's just a link time decision. You don't have to rewrite a single line of source code to relink your object file to an OpenSHMEM layer instead of an MPI layer. We also looked at two-sided MPI, and we also tried the gold standard for Coarrays, which is the Coarray Fortran. And we used up to 25,000 processes and found that for every data point, OpenSHMEM was outperforming MPI. So having the flexibility to make that switch really matters. And also, I don't know how well you can see it, but the graph that's on the left, or in both graphs, the orange dots are the Coarray Fortran running on top of MPI, and the CAF-SHMEM is the blue dashes. So in every case, OpenSHMEM outperformed MPI. But also, really importantly, notice that the orange dots don't continue to the highest number of processes. And that was because of that problem with the MPI implementation. We couldn't get beyond about 2,000 cores without the initialization time becoming so expensive that it just wasn't even worth doing the simulation. So having this ability to swap what your underlying communication substrate is really can make a big difference. And then I'll just mention some newer projects. I just started working, collaborating with David Torres at Northern New Mexico College and his student, Dominic Martinez. And we're developing an application we call MACHA, Motility Analysis of T Cells Inactivation. And in MACHA, what we're trying to do is match the speed and turning angle distributions of T cells, which are important in the immune system as they move through tissue. And the value of simulations in this context is that you can explore larger spatial volumes and larger regions of parameter space than you could in vivo, like if you were using, say, microscopy. So the simulations can be really helpful. So far, in terms of programming models, we're using Coarrays for the halo exchanges. We talked a bit about halo exchanges yesterday in a 3D diffusion PDE solver. And we're beginning to explore using do concurrent for automatic GPU offloading, which currently the Intel compiler can do, the NVIDIA compiler can do as well, but with some restrictions because the NVIDIA compiler doesn't support a lot of Fortran 2018. And from what I understand, HPE is working on that capability as well. So just as one highlight, the 2D heat equation solver that we're using in this tutorial was developed as the initial prototype for use in MACHA. So what you're seeing is not just toy code in a sense. It was an early stage of development for an actual scientific application. And then last thing I want to mention, another new frontier project that I started since coming to Berkeley Lab 2 years ago, just beginning to do a bit of work in deep learning. And the initial target application for this work is ICAR. We want to see if we can replace the cloud microphysics model, which is the part of the code that predicts whether liquid or ice water will form at a given point in the atmosphere, and see if we can replace that with a neural network as a proxy. Because once we got Coarrays into the code, that enabled the code to go to scale into distributed memory. Before introducing Coarrays, it was a shared memory OpenMP code. But it turns out that 90% of the runtime is in that cloud microphysics model, which is pretty close to being embarrassingly parallel. If you set it up right, you can have each of the grid points be independent for the cloud microphysics. And we believe we'll be able to train neural networks to replace the microphysics model. So one of the ideas is that by writing the software that does the inference, in other words, that uses the neural network to make predictions, by writing that software in the language of the application, we can potentially do in situ training of the neural network so that as we're doing a simulation with ICAR, we can, at every time step, use the new data that we have to iterate and train the model. And then by the time we finish a simulation, either if we've simulated long enough, we have a fully trained model, or at least we have a pre-trained model that we can then export to help us in terms of convergence and faster training if we decide to use an external package like PyTorch, for example. So again, here also exploring language-based parallel and GPU programming, a lot of use of array statements. One of the nice things with array statements in Fortran, if you have an array A and an array B and you say A equals B, you're not doing the ordering of those assignments of each element that you would with a do loop. I still see a lot of code out there where people write nested do loops to do relatively simple computations on multiple dimensions of an array, when oftentimes that 5, 10, or even 15 lines of code could be collapsed to a single line of code or a few lines with array statements. So I highly advocate for those, both because of their compactness, but also because it's a way of expressing parallelism at a fine-grained level. We also use a lot of elemental procedures. So elemental procedures are such that you write them so that every argument is a scalar, but then you can pass in an array and the compiler will simply apply that, that procedure to each element. And if it's a function, give you an array result. And so again, that's a situation where you're not ordering the computations, you're just saying, do this computation on all of these elements. So I think all the different ways that we have to avoid ordering computation are extremely useful in terms of both clarity, but also enabling the compiler to do things like GPU offloading or multi-threading or various other technologies to optimize the code, which of course also leads us to do concurrent, which does the same sort of thing. The other thing I'll mention is that we use a functional programming pattern that I've developed largely with Brad Richardson, who I mentioned earlier. And every procedure in this library is pure, including even the inference and the training procedures. And that was one of the main things that actually led me to develop this library. Initially, when I started this project, I expected to just use existing software. There's one Fortran package out there that I know of that does neural network training and inference, but the procedures aren't pure. So the important thing about that is not that we're trying to keep to some level of virtue in how we write code. It's, first of all, there's a certain amount of clarity in it because all of the functions that are part of the language are pure. So when you're writing pure procedures, you're writing things in a way that will feel natural to your users because it won't feel different for them from calling the functions that are part of the language. And so the other really important thing that ties into this discussion is that in order for a procedure to be called inside do concurrent, it has to be pure. And I think I mentioned this briefly yesterday, but just as a reminder, pure procedures have no side effects. They only map from inputs to outputs without affecting the state of the computer in any other way. So you can't do IO, you can't do image control statements, things like that. And so I realized recently that we also have a very obvious opportunity to take this code parallel. This falls into the category of what I described earlier, where we don't expect that we're going to need coarrays, but we do want to take the code parallel. Oftentimes when you're training neural networks, you train based on many batches of input-output pairs, training data. And you do a forward pass through the network and a back propagation pass, and that forward and back propagation pass is independent for each input-output training pair. But if you were to adjust the network, so the network is basically a bunch of connected nodes with weights and biases. If you were to adjust your weights and biases every time for every input-output training pair, then it effectively amounts to zigzagging in this really high dimensional space. And so to ameliorate that and improve convergence, oftentimes people average the updates across a mini batch, and we could therefore compute that average quite easily with a cosum and start doing parallel training. Okay. So this is the training code that's in Inference Engine, and I apologize for throwing this wall of code at you. The reason I wanted to put all of this up is, first of all, to say that training is not that hard. This is pretty much the entire training algorithm. When I first started down this path, I was concerned that we shouldn't try to compete with PyTorch or TensorFlow. Now that I've actually gotten into it and looked into the training, it's not nearly as hard as I thought it might be. So in, what is this, 100 and, oh no, less than that, it looks like 53 lines of code, you can train a neural network in using mini batches and mostly what you're doing is computing gradients of a cost function relative to some weights and biases. So just to give you an idea of what's here, as I just mentioned, since we're iterating across and within many batches, that first of all means that we can do training in situ at application runtime, because we could decide just to have a mini batch of one, for example, if we only got one input output pair at every time step. Although actually in this case, as long as all the good points are independent, we're getting a lot more than one. So we could treat whatever we get at one time step as our mini batch. And it also really improves our workflow to be able to do all of this in Fortran. Before we started down the path, so at one point I decided to write inference engine just to do the inference. That's why it's called inference engine. And I thought, okay, at least it would be great to be able to have a pure inference procedure that I can call inside do concurrent. And the goal of inference is to make computation cheaper, right? If it were more expensive than the cloud microphysics model, there'd be no point. So you wouldn't initially think that inference is necessarily even worth offloading to a GPU or multi-threading or anything like that. But once you have a large enough batch of inference, so up to now we've been training 8 neural networks on which we need to do inference at each grid point in a 3D grid at every time step. So that's what I'm referring to as large batch inference. And in that context, it can be very useful to have an inference procedure that we can call in a way that parallelizes. Okay, so basically everything in this short training code is making heavy use of array statements. You can see things like 1:n of vals. This is saying I'm computing here the gradient of the cost function relative to the biases in my network. And I want to work on at a given layer. So L is the layer. At a given layer, I want to work on the elements of this array that go from 1 to whatever is the number of neurons in that layer. So this is where, if I weren't using array statements, you'd see another nested loop here. And once we get past that array statement, the next thing we have is a do concurrent that has itself an array statement inside of it. So essentially the only serial logic in this training algorithm, the only just plain old do loop, is the one that goes from layer to layer. And that is largely unavoidable. I could imagine some ways that you could possibly write code, especially if you were, had like a task scheduling framework or something, that you might be able to write code so that you didn't have to finish a layer completely before you start the next one. But for the most part, that part of the logic is inherently sequential. And so that's why you see the one sequential loop there is the loop that's going from looping through the layers. And I guess another reason I thought about writing this kind of code in Fortran is that I thought there was a reasonable chance we could beat PyTorch or TensorFlow, but initially I really was kind of shy about even saying that. It sounds like hubris. These are developed by these big billion-dollar companies. But then a couple months back, Andrei Sertic, who develops a Fortran compiler, by the way, it's called L-Fortran because when he started developing it, he was at Los Alamos National Laboratory. And he was just toying around with inference, and he implemented the GP2 inference method in Fortran and found that in only 300 lines of Fortran, his code was faster than PyTorch. So I'm sort of emboldened now to see if we can beat the big boys. Okay. The next topic is teams, and we're not going to actually make much use of teams today. I have one simple example, just a test that can show you the basics of how teams work. But in terms of explaining the features in the language to you, even with some of the simplest features like calling this image to get your image number, it turns out that one of the optional arguments that you could have to this image is a team number or a team type object. So for that reason, more than any other, it makes sense for you to at least understand the concept of teams so that I can introduce other concepts to you that depend on teams, at least depend on teams optionally, put it that way. So teams are simply an ordered set of images created by executing the form team statement. Or if you haven't executed a form team statement and your program, since the program launched, then you're in the initial ordered set of all images, which basically is one global team. Michelle?
Hi, Damien. You have an interesting question on Zoom. So Louisa is asking, how does this compare? I think probably referring to the PyTorch. How does this compare with hardware acceleration?
That's what I'm really excited about studying. So I have a student working with me this summer. He got a late start, so he's only been here a couple of weeks, but we are specifically doing runs at the University of Oregon, where Samir Shinde is. Samir is the one who set up the AWS instances for this tutorial. And with the Intel compiler, so unfortunately you can't do it with all compilers just yet, but with the Intel compiler, if you're running on an Intel chip and using Intel GPUs, so that's why we went to Oregon, because Perlmutter has NVIDIA GPUs. So then it will automatically offload do concurrent. And so I just showed you the training code. There's tons of array statements in there, tons of uses of do concurrent. This is what we want to explore. The student just got his account at Oregon a few days ago, so we haven't gotten there just yet. I will say, in the interest of full disclosure, sadly, life at the bleeding edge of modern Fortran, I guess since I said bleeding edge, you will nick yourself often. I fully expect that one of the very first things that's going to happen is he's likely to encounter a compiler bug, and we'll have to isolate it and submit bug reports and then develop workarounds, and we'll get back to you. But part of the issue here is that the Fortran community, I think, needs people to explore things like this earlier, because part of the reason that there are these bugs is not enough people are trying these features out and reporting bugs. So so that is a to be determined question. It's actually as I see it, part of the research is exploring language-based parallel and GPU programming, and hopefully we're able to get good performance when the Intel compiler does the automatic offloading for us. So teams facilitate the execution of image sets independently from other image sets. For example, if you execute a sync all in a team, then it only synchronizes across the current team. And Michelle?
This is a question about teams.
Great.
So David Torres is asking, when do the team images communicate with each other?
So you can do communication within a team the same way that you would if the images were on separate teams. However, I think maybe the most important point is that you'd like sometimes for certain parts of the code to be asynchronous relative to each other. So the early inspiration for teams was actually climate models. Imagine you have an ocean model, an atmosphere model, a land ice model, a sea ice model. These are all operating on different timescales. You might want for one to be able to take 10 time steps, on its own without having to synchronize across the entire model. And so the idea of teams is that things like synchronization become, local steps, but it is still possible to communicate across teams as well. So unfortunately, I don't have an example that gets that involved, partly because the team support in G-Fortran is pretty limited right now. And so not that many people would have access to it. The Cray compiler does have full support for teams, and the Intel compiler does as well. So in order to use teams, you need to use this derived type that the language provides. It's in a module called iso-fortran-env that the language defines, the standard defines. And it's an extensible derived type, so you can have that as a parent type for various child types that you yourself write. It has private components, so you don't get to touch what's in there, but those components describe a team after the successful execution of a form team statement. So basically, the team type object has information about what images are part of a given team. And here we're just showing some array accesses in each team. Michelle?
So another question we have, this one's on Slack. Andrea is asking, is an image referring to part of an array?
Sorry, okay, we did talk about this yesterday. I thought the way Amar did a summary and recap of his presentation yesterday was really helpful, and so I probably should have done a bit more of that myself. So, and the way a Coarray Fortran program starts is that multiple copies, independent copies of the program are created. They're essentially identical except for a few details, like each one knows its own image number, but otherwise they have the same the same types of and shapes of data structures and what have you, but they launch independently. And so you could think of it as just a replica of the program. So it's the whole program, basically. Hopefully that clarifies it. Okay, if you are familiar with a similar concept in MPI, then this might be helpful, just showing that the kinds of commands that you would use in MPI to do the same thing. In fact, if you look at the way these statements are supported in open Coarrays, they are using these MPI features. So the form team is like an MPI com split. A communicator is what you use in MPI to communicate across different processes, different ranks. And I guess in MPI, what we refer to as the team number would be analogous to a color. So I'm showing teams here in different colors, and I'm using the solid lines to indicate that the default communication mechanism, once you've done it, once you've grouped into teams, is within your team, but there is still an optional way to communicate across teams. And once you get to an end team statement, then which one is the default, switches, basically. Okay. This is just a little test code that is in this short, it's a 4-page extended abstract that I wrote with James McCrate at NCAR and Alessandro Fanfarillo, who I mentioned earlier. And we were just beginning to explore teams. We weren't able to develop the funding to carry this work forward, but the basic idea was we wanted to be able to take an MPI code and do parametric studies with it, where we'd be able to launch multiple MPI simulations. And we were going to use the fact that we know that under the hood, Open Coarrays is using MPI. And so we wrote a tiny extension to the language, because in the Fortran standard, there's no assumption about what is actually supporting Coarray Fortran. So there's no assumption that there's MPI there, and in many cases there's not. With the Cray compiler, for example, they have their own proprietary communication library. But we wanted to explore what would happen if we had a main program that was using teams to drive individual simulations that were that were run with MPI. And this is a little test code that we had in that paper, where we're forming a team that, and our teams are we're forming 2 teams that are comprised of even and odd numbered images. So this is my mod function based on the team number to figure out which team I'm on, which team a given image is on. And after we form the team, then we change to that team. So this home is, you can see up above, the team type. I think this target is probably not necessary in the standard Fortran, but it probably has something. Target basically says it's okay to associate a pointer with this object. And my guess is that's an artifact of something that we were doing because we didn't have full compiler support at the time. And I have these assertions in here just to kind of give you an idea of what should be true at different points in time. When you start the program up, the initial team number should be -1. That's what tells you that you're in the initial team. And once you've done your form team and your change team, the team number should match the team that you chose to be on. And then once you hit an end team, you should be going back to the standard initial value for the team number. Okay, so now we can finally talk about a couple of the simplest functions that are in the language, like this image, which actually has 3 different function signatures. Most often, I use one that doesn't have an argument at all. So on this slide, I'm using square brackets to indicate things that are optional. That's a common approach in the standard. I'll switch to a slightly different notation a bit later. But so we can have this team with either no arguments, or you can have a team object, or you can put in a coarray and have a team object. Michelle?
Oh, I'm sorry, you didn't have to interrupt the middle of your sentence, but
That's okay.
We do have a question about teams. Would teams be similar to the color function within MPI com split?
I believe so. I mean, that's what I was trying to show in this slide. So on the right, you're seeing the corresponding MPI call that you would write if you were doing essentially the same concept, but instead, if you're using Fortran and just standard Fortran, then you use form team and change team to get to accomplish the same thing. And in fact, that is the call that's happening under the hood in Open Coarrays, which is the parallel runtime library for G-Fortran. Hopefully that answers it. Okay, so there's also an image index function where you can pass in a coarray and a set of co-subscripts. So far, whenever we've seen coarrays, I've only shown it with one subscript, one codimension inside the square brackets. You can have multiple codimensions. And so I'm showing an example here. Can you guys see my cursor?
Yes, we see the
we
cursor.
can. Yeah.
Okay, great.
Mhm.
Okay, good. So at line 3, then I'm showing one example of a coarray A. These are both static coarrays, meaning their shape and size is determined when the program launches. The asterisk here is indicating that we can't completely determine it at compile time because it depends on how many images we're running. But I'm saying that for A, it's a scalar coarray. Scalar meaning if I drop the square brackets, it looks like a scalar. B is an array coarray, meaning that if I drop the square brackets, it looks like an array. And so I'm saying for A, I want my lower bound on the one codimension that I have here to be -1, and then up to a number determined by how many images there are. For B, locally, I always want to have 10 elements, but let's say what inspired this code is I'm thinking about like a 2D Halo exchange. So in our heat equation solver, we're only partitioning across one dimension, the X dimension. If instead we were partitioning in 2 dimensions, which is what the Chapel heat equation solver is doing, I believe, then you might want to have, and you want to do communication between those, you might maybe want to have, 2 codimensions so that you could reach back along, the X direction or forward, and same thing along the Y direction as well. It gets pretty tricky though, depending on how many images you end up using. So this is an artificial example, mainly just for teaching purposes. Over time, I've evolved towards just using one codimension in almost all cases, because as you can imagine, if you had 1,000 images, then there might not be a lot of use to the analogy that I just gave. So I haven't found a ton of use for the multiple codimensions. I will say that the originator of Coarray Fortran, Bob Numrick, his basic idea of allowing for multiple codimensions was similar to an idea that they have in Chapel with locales, I believe. The basic idea was that the first codimension might range from 1 to the number of chips on one to the number of cores on a chip. The second one might range from 1 to the number of processors on a node, and a third one might range from 1 to the number of nodes. And so you could tell something about the computer's architecture from the way the Coarray gets laid out, but the standard doesn't say anything about that. So it's not guaranteed to you. My understanding is that with the Cray compiler, you do end up getting something similar to that. But since it's not standard, I pretty much just end up in almost all cases using just one codimension. So here, this program, what I'm going to do is have basically all the actions going to happen on whatever's the last image, the one with the highest image index, and we'll see what it means to pass in the coarray A. So I'm basically saying, okay, I'm the last image. Where does my index fall? So each of these is going to give me an image index back, and we'll see what that means in just a minute when I run this. This code, for a lot of the really simple examples that are just a few lines long, we don't have that in the tarball that went out to you guys. If you after the tutorial wanted to work with this on your own, it's just a few lines to type, but we could also maybe update the tarball afterwards. So then there's this image index, where I can pass in a coarray and a list of post subscripts and say, well, what is, if I were to just number all my images, in a sequence, one-dimensional sequence, then what would be the index for this element of this coarray, or for this element? And you can see here, if you think about the way I was just talking about this for doing Halo exchanges, you can see I'm trying to figure out like what's the origin, sort of, what's my index in a sense. And there are these L cobound and U cobound functions that are analogous to the L bound and U bound functions that are part of the language. So I can get the lower bound of my codimensions from those functions. So this is me running the program that you see up above and naming the executable image enumeration. And now I'm going to run it in 5 images. Okay, and we'll talk about these values in a minute. Now I'm going to change that number 5 to 1. So just launch 1 image and see a different result because the numbering where I fall. Well, one problem is that in the case of 1 image, some of the things that I have there, like putting element 3 here, don't really make much sense. So this is what we're trying to do. So with those 2 dimensions, you could imagine, so mapping out B as such. Now remember, in the first case, I only ran 5 images. So if I were to count my way through these, then at least I have enough to get to that 0, 0 element. So that's why for this case 0, 0, I can see that I get 5 there. And we can see the low LCO bound and UCO bound give us what we'd expect. So those are all the same. And then for array A, the 3rd element, since I'm starting, actually this should start with -1 here. And so since I'm asking for the 3rd element, let's see. I haven't used this feature very much, and it's slipping my mind now exactly how to calculate these. Michelle, Saved by the Bell here.
Yeah. So I hope you don't mind me interrupting, but there was a question on Slack. Somebody's asking, what happens when an image produces an error during execution? How does the rest of the program such obstacles?
Good. So in fact, when we get to, okay, here we go. The next thing I was going to talk about is synchronization. We saw a sync all statement that didn't have anything after it. So now I'm switching to a notation where I'm going to color the things that are the part of the statement that have to be there, and then the things that are in black are optional. So let's say, for example, you tried to synchronize and for some reason it didn't work. Maybe one of the images has stopped, already, and or failed or what have you. Then you can get back, either if you haven't added the optional features here, then the program will crash. Or if you have, the program will continue and it'll give you a stat value. This is an integer, and it'll give you a stat value and an error message, which is a character variable, a string, that indicate what happened. So you can then figure out how you want to handle it. Okay, in addition to sync all, which is a barrier.
Oh,
yes. Something else?
I also wanted to let you know that you're halfway. You're at the halfway point.
Okay, good. Thank you.
Mm-hmm.
Okay, so in addition to sync all, which synchronizes across all of the images, at least in the current team, and there's also sync images where you can just synchronize over an image set. So you're going to pass in an array of values here that this would be useful. Again, if we think back to the Halo Exchange example, this is useful if maybe I only need to synchronize with my nearest neighbors, right? In reality, I don't know if it makes a big difference in my experience to use sync images, because at least in the example of Halo Exchange, is because what happens is I'm waiting on my neighbor and my neighbor's waiting on their neighbor, and it, in my experience, doesn't end up being too different from doing a sync all, but it is a slightly looser form of coordination across images that could possibly have some performance improvements associated with it. If you allocate or deallocate a coarray, that's also a synchronization point, a barrier. And that also includes if a coarray gets deallocated implicitly. For example, there's a block construct in Fortran where you can have the statement is block and then in block. And so if you have a block of code and you declare a coarray inside that's allocatable and you allocate it, it's going to implicitly get deallocated at the end of the block. Or same thing in a procedure, it'll implicitly get deallocated at the end of a procedure. If it's local to that procedure, there'll be synchronization at that point as well, which is important because given that we have one-sided communication, we want to make sure that if other images are needing to access that data because they're in the same block, you wouldn't want the data to go away until everybody has reached the end of the block. So a stop statement is also a synchronization point. We've talked about that's a normal termination. Stop and end are both normal termination. We talked about that yesterday. Move alloc is something that we're not going to have use for. I just wanted to put it here for completeness. Essentially, you're taking memory that's associated with one name and moving it to another name. So that, of course, if it's a Coarray that you're moving, then that's an important point to synchronize as well. And I guess because of what I just talked about, any statement that ends a block or a procedure then becomes a synchronization point if there's a local Coarray. But I don't find that I typically declare local Coarrays inside procedures. That I think would be a significant performance bottleneck. So I avoid it if I could. There's also a sync memory statement that I'm listing it here by saying it's deprecated. There is in the Fortran standard a term called obsolescent. And in fact, if you're reading the standard, anything that has been declared obsolescent will be in a smaller font. And it's a way of saying there are better ways to do this, probably because this feature has been superseded in more recent standards. Things like common blocks are obsolescent, for example. And then there's also features that have been deleted, not very many. Fortran is typically very backwards compatible. Most standard conforming Fortran 66 programs are also standard conforming Fortran 2018 programs. So there's no official deprecated keyword in the standard. However, there's a book, Modern Fortran Explained, that is one of the best references for understanding Fortran. And it's written by Metcalf, Reed, and Cohen. Metcalf used to be on the committee back in the 1990s. As I mentioned a while ago, John Reed was the convener of the committee, and Malcolm Cohen is the editor of the Fortran standard. So all changes that happen to the standard, Malcolm makes, and he has savant-like, comprehensive, exhaustive knowledge of the standard. And he almost single-handedly develops the compiler for the numerical algorithms group, NAG. So for my purposes, if they deprecate it, I'm not going to use it. Basically, the idea is it's too tricky to get it right. So not a feature that I use in my own code. Other image control statements, which statements that order segments of sequences of statements, so are locked. So you can have a variable that only one image has access to at a time if that image has locked it until that image unlocks it. You can also have critical blocks. Critical blocks are blocks of code where only one image can execute that code at a time. So that can be very helpful for things like file IO. You can also, I guess, form team, change team, end team that we've seen already. Those are image control statements, meaning they impose some ordering so that you can know that a certain segment of code on one image executes before a certain segment of code on another image. So because these are used, things like locks are used for coordination across images, they have to be Coarrays. And the lock variable there is of lock type, which is something that the language provides in the ISO Fortran env module. And it has to be a Coarray, but you can extend it. You can write a child type that it inherits all of the behavior and state of the lock variable. And then towards the end, we'll get to events. And events are a much looser form of coordination across images than synchronization. It gets us something that is at least closer to the really nice feature that you've seen in UPC++, which is futures. And futures are a lot more flexible. You can do a lot more with them than you would with events. But basically with an event, I can post information to another image and tell that image, say, for example, that data is ready for pickup or that I've already put data on the other image. And the other image can wait on that event. And so because they're designed for coordination across images, events, so an event variable, which is of event type, also has to be a Coarray, and it's a derived type with private components. Okay, the next set of features I want to talk about are collective subroutines. And the idea of collective subroutines is that these are computations that have to happen on all of the images in the current team. And so every image has to call the collective, and every image has to invoke the collective in the same statement, I guess the same sequence, and participate in this collective computation and communication that happens. And so there are 5 collectives in the language. Co-sum, as the name implies, is doing a sum across the images. Co-max is looking for the max value of the first argument A. And you can either by default get the result on all images, or optionally, if you pass a result image integer, you can have the result only appear on one image. And all of these have a stat and an error message variable as well. So if something went wrong when you tried to do the collective and you didn't have stat or error message there, the program would crash. Otherwise, if something went wrong and you have those there, then you'll get a code back in the stat variable and a message back in the error message variable that tells you what happened. So code min is doing a minimization operation reduction. And then code broadcast is taking the data that's on one image and broadcasting it out to all the other images in the team. And co-reduce allows you to extend this feature set by writing your own operation. And operation is basically a pure function that you write that does some sort of reduction on the data. So we'll go through each of these in a little bit more detail. For co-sum, the argument, of course, has to be of numeric type because you need to be able to apply the add operator, and has to have the same shape type. And we're not using type parameters much in this tutorial, but you'll see me declare a variable as real, so basically floating point, and you'll see me put in parentheses rkind. That's me specifying the precision of the variable. So that rkind number is a kind parameter, so it's a parameter on the type, on the real type. You can also have parameters on your own derived types. So the argument is in out, meaning the value coming in matters, and it will change the value or could change the value on output. And the argument result image, we've talked about a bit, that's intent in, so it doesn't get changed. Let's look at how this operates. So time going downward on the left there. We could see 2 teams executing co-sum here, and the co-sum only happens within a team. So basically, if what's going to happen is that if we're applying it to an array, I typically most often use it for scalar. If we're applying it to array, then we'll get an element-wise sum. So 0 plus 2 plus 3 gives us 5. And since there's no result image here, every image gets the 5, right? And so that's the same thing for all the images in the team, is also in team 2. There's sort of the same pattern there. Same thing for all the other elements. Okay. Co-max, very similar, must be of numeric type. None of these can be co-indexed objects, so you can't go out and grab remote data and put it in as the argument there. You can't have square brackets on that first argument. So again, it's doing an element-wise maximization. So you can see the first element there is 1, 2, 3. So the maximum number is 3. So you end up with a 3 here. Co-min, same idea. 1, 2, 3. So we end up with 1 on all the images. And co-broadcast. Now this gets us to something interesting because the ones that we looked at so far all had to be of numeric type. This is the first one we're seeing where you can define your own derived type. Now, that derived type has to have the same shape if it's an array and the same dynamic type. We haven't talked much about object-oriented programming in this tutorial, but basically if you have a collection of derived types and let's say one child type extends a parent type. So if you're familiar with inheritance in other languages, we call it type extension in Fortran, then the variable that you're declaring could have different types depending on when a given line is executing. Let's say you're passing the variable in as an argument. What the actual type is that's being passed might be different from one call of the procedure to another. So whatever the actual type is at a given point in time is the dynamic type. And this was Brad Richardson very recently, just over the past week or so, had a really interesting idea about how to use this co-broadcast to get two-sided polymorphic copies of objects across images, because since it's saying here that they have to have the same dynamic type, but it's not saying that it can't be polymorphic. It's not saying that that dynamic type can't vary from one call to the next. And so one idea to have some form of, ideally, what we'd really like is to be able to just put an object from one image to another and have the dynamic type get set on the remote image when that put happens, but that's not allowed in a language. And so one way around that would be to form a team that's just the two images that want to communicate, and then use the co-broadcast as your communication mechanism. Now, the interesting thing about that is it is a great workaround for the problem, but at the same time, it also shows the problem with two-sided communication. Because in order for this workaround to work, you've got to execute a form team and an end team, and we've now seen that both of those are synchronization points. And so it's something that's very useful when you need it, and we do think we'll need it in a library that I'll show you a bit later. But it would be much better to have actual one-sided communication of polymorphic objects where we could set the dynamic type of an object on a remote image just by assignment, because that would be one-sided and it wouldn't involve the synchronization points. So co-broadcast here, we're saying the source image. So I guess the second argument here, instead of result image, that we now have source image, saying where the data is coming from. And so here we're saying that the source image is image 1. So after execution of the co-broadcast, every other image in the team has a copy of what image 1 had in that array. And lastly, co-reduce. As I mentioned, the second argument is an operation. So it's a pure function that you would write that performs some operation. And you have to write a procedure that does something that is, let's see, mathematically associative, is what I was looking for, in order for it to serve as an operation. And I have a simple example we can go through here. My thought was to do this as a hands-on, but I think in the interest of time, since we're already past half time, I'll maybe just talk you through it for now, and if we have time, we'll come back to this. That way we can get further along with the most complicated example you have, which is the heat equation solver. But this is something that I actually have in a library. The sorcery library is basically just a grab bag of little tricks that I might come up with for one project, but I know that I'd like to use them again in another project. And so one example of that is user-defined collective subroutines. In fact, this co-all is, at this point in time, I think the only one that I have. Actually, well, there are others that are, I guess, attached to different parts of the library. But if something in this library grows and becomes a sufficiently large and useful set of features, then I'll oftentimes spin it off into its own library. So this is just kind of a random collection of things. But you might be familiar with the all function in Fortran, where you can pass in a logical array, so true and false values. And the all function only returns true if all of the elements of that array are true. And oftentimes I use it where I'm constructing an array on the fly and I have expressions in each element. I'm just trying to check to see if all the expressions are true. So sum is useful within an image. All is useful within an image. So it can be useful to have a co-all that checks for true across all the images. For example, in a test suite, you might want to check to see if all the tests pass. So this also gives me a chance to talk about the way that most of the codes that you have in the repository are structured. Typically, when you see a module, those will just have interface bodies, which is what you see from lines 5 through 8. So this is just telling me the signature for this procedure, the name, what type of procedure, if it's a function or subroutine, the arguments, various attributes of those arguments, like the fact that this is intent in out, and also the type of the argument. Okay, the actual implementation of the procedure, I like to keep separate in a submodule. And the submodule then, optionally, you can repeat all of the interface information. I generally choose not to. So if you don't repeat it, then you put module procedure, and here's the COAL subroutine that I'm writing. And the basic idea here is that I'm going to call co-reduce, pass it in whatever A argument came into the COAL, and then I'm going to pass in a pure function that is my operation. And basically it's a logical AND operation. So it takes two operands, and any operation that you pass into co-reduce has to take two arguments. There's a left-hand side and a right-hand side. And then the result that's going to give you is basically the left-hand side and the right-hand side. You're applying the AND logical operation to those two logical variables and getting the result. So what I could do is at least run this one for you. So I'll come out of screen share and switch to a terminal window. Okay. Is that font big enough? Can everybody see that? Okay, so these three codes are the ones that you actually have in the tutorial tarball. And I've got a separate directory of just some very small codes here. So here's the COAL example that we just looked at. So then in the main program, you'll recall that I use associate for what I call runtime constants. If I associate a name with an expression, and one degenerate case of an expression is just a function reference. So when I associate a name with a function reference, then that gives me immutable state. It means that I can't accidentally change this value, at least within the scope of this associate block where it's defined. So I'm starting off with my operands as true on every image. And so then I'm calling COAL, and I would expect to get true then, since they're all true. So we should see that image one is going to print out T for true. And then I'm having the last image set its operand to false. So now every image has true except the last one. And now when I call coand, I should get false. COAL, I should get false, because there is one image that has a false value. So we'll see that we should see F print out for false. Did I do that right? Sorry, I meant to do a -O there. Okay, so just what we expected. All right, I'll switch back
So
to.
Damien, you're running this on your laptop. Is this?
Yes.
So it's just starting up a process per image?
Yes, it started up 5 processes corresponding to 5 images, exactly.
Okay,
But I only had image 1 print,
got it.
if I recall correctly. Yes, image 1 is printing. Okay, I'll switch back. Oh, first I need to switch to play mode. And how much time do I have left, Michelle?
You have, I'm doing math. Let's see, 55 minutes.
Okay. Oh, there it is. Okay. When I try to click to move this, it goes to the next slide. All right, good. So I apologize again, the wall of code here. I just want to walk you through a few blocks of the code that are in the heat equation solver, since this is sort of the most complex code that we have in the tutorial. And kind
Damien,
of tell you what.
I'm sorry to interrupt.
Yes.
I did math very poorly. It is 11:57 right now, and you have until 12:20.
Okay, perfect.
20 minutes, yes. Big difference.
Okay, good, thanks. Okay, so these use statements here are pulling in modules. My pattern is to put _m at the end of a module name. and pulling in specifically certain types. So I put an _T at the end of a type name. And then implicit none, hopefully anyone who's familiar with Fortran uses that everywhere. It just says that I have to declare the type of everything I'm working with. I don't want I don't want the compiler to do any guessing. And then I have a bunch of declarations here. This is running the same size problem as the UPC++ and Chapel solvers. However, it's using a different initial condition. I call this procedure define to set that initial condition. I'm solving in a domain that's 1 by 1, so it's 1 on a side. This is a precision specifier that I'm adding here that I pulled in from another module up top there. It's basically going to give me double precision in this case. And then I'm setting the boundary value. It's constant all around the boundary. And then I'm setting an internal value that covers the whole internal part of the domain. And that's the part that's different. So you won't see the same average temperature when you compare this code to the Chapel and the UPC++ code, because they set the internal temperature on a smaller square. And then I'm setting the number of grid points in each direction. And this is using a pattern that I picked up from Dan Bidachea, who's with us in my group and here in the tutorial, which is that I used to a lot of times include synchronization inside some of these procedures. And I've kind of backed away from that, so that the new pattern that I'm beginning to adopt is that unless there is this one case here where I have right in the name, you know that allocating a Coarray is an implicit synchronization. But otherwise, unless it tells you that in the name, these are all procedures that you should expect will be asynchronous. And so this does the definition of the temperatures. And then we actually talked through the basics of this code yesterday. And so I think what I want to do is move quickly to the hands-on exercise, because we've also already talked about collectives. And yesterday we talked a bit about the Halo exchange. So one thing I would like to show you that you can do with this code, because of the ability to use user-defined operators in Fortran, is that you can very rapidly move to different types of numerical algorithms by recombining these operators. In my private business, I work with a company where there's an engineer who was developing Fortran 90 code in a much more traditional, non-object-oriented, non-functional style. And we were hired to advise them on modernizing the code and eventually to replace it. And I remember him telling me that when he had to switch from this sort of time advancement scheme, which is the lowest order of accuracy that you could use for time advancement, to a 4th order accurate Runge-Kutta scheme, it was about 2 days of work. And one of my main selling points for introducing this style of coding was that making the move to a higher order scheme, at least within the certain family of schemes, is essentially trivial, just a few lines of code change. So this is in the README. It describes what I'm talking about, and I'll just walk you through it in the terminal window. Okay, so let's run the heat equation solver. I'll run it in 4 images. Oops. Okay, and that took 8.5 seconds. And we can see the temperature that we get out there, 1.99559. And what I'd like to do is to move to a more accurate time advancement scheme. And the way I do that, so this is called, any of those of you who might be familiar with numerical analysis, this is called forward Euler or explicit Euler. I talked yesterday about how we're updating the temperature, and our update is just the time step times basically the right-hand side of the PDE, right? Rather than doing a full step at once, there are these schemes called rungekutta, or you can also think of this as like a predictor corrector scheme, where I say, let's just go halfway first. And I'm getting an estimate that's halfway out in time. At least it's one way to think about it. You could think of the half as just multiplying the dt. And now that I have that temperature estimate, I'm going to go back. Let's see, actually, I'm going to update that. Actually, I got that wrong, sorry. There we go. Yeah, I'm going to go back to, the original temperature that I had, but instead of evaluating the Laplacian at the old time step, I'm going to evaluate it at that halfway point. And if you look up Rungekutta schemes, and this is a second order Rungekutta scheme, there's some nice graphics I probably should have included here to kind of to show you why that gets you a more accurate time step, a more accurate step. But the basic idea is that your error for this first scheme that we're using is proportional to dt, the amount of time you're stepping forward. Whereas with this new scheme, it would be proportional to dt squared. So if dt is small, you're going to get much more accuracy. So I will add p half. So we changed our declaration, we changed the time step line, and we added one line. And that was it. Okay, so I don't have an analytical solution to prove to you that this is more accurate, but you can see that it's close to the other value. And if we, we could do things like a study where we, use that same kind of scheme on a problem where we know the solution and see how the error varies as we change the time step. And it should get closer to the answer quadratically with this new solver. This is going from first order to second order. Fourth order, which the engineer I was talking about was doing, is not that much harder. It would just add a few lines of code. So for something that in a traditional style code would take him, 2 days, mainly because there were lots of global variables that were accessed by lots of different procedures, whereas we use objects with, private data and what have you. You can see that with this approach, it's trivial. Okay, let's go back to the slides. And I should have, what, about 12 minutes? Let's see, 14 minutes. Okay, so a bit more about coarrays. We've seen several different types of coarrays already. We've seen a non-allocatable coarray in the hello world. So all of the memory for this gets laid out at compile time or program launch. And then we've seen in the Halo exchange that we looked at briefly yesterday, we've seen a dynamically allocatable coarray. You can also put coarrays inside derived types. This can get a little bit tricky. So you'll see an example of this. So I published a book in 2011 called Scientific Software Design, The Object-Oriented Way. The book is mostly serial code. There is just one coarray example in the final chapter of the book. I will say, by the way, when we talk about how these programming models are easier to write, when we submitted that book to the publisher in 2010, there was no compiler on the planet that could handle the code. My co-author on the code was Jim Zia, who was both on a standards committee at the time, the Fortran standards committee, and on the IBM compiler test team. And he had encyclopedic knowledge of the language. So we had this 400-line code that was solving a one-dimensional unsteady partial differential equation called the Burger's equation. And that was the one code in the entire book that we couldn't check before the book went to press. 2 years later, when I finally got my hands on a compiler that could actually compile the code, it ran correctly the first time. I ultimately discovered one bug that only comes up if you're just running a single image, but otherwise the code was essentially perfect. So there aren't many languages or programming models I think you could try that with, like publishing a 400-line parallel, object-oriented, functional, partial differential equation solver with the expectation that it will work because what you're doing is sufficiently clear, or maybe Jim is sufficiently smart. So one thing that does get tricky though is that you cannot return a coarray, or for that matter, an object that has a coarray inside it as a function result. Because if you did, that would end up imposing an implicit synchronization. The committee tries to do things so that you can't shoot yourself in the foot too easily and cause major performance bottlenecks. So, this sort of syntax that I've been showing you, you do have to be careful where every time within those operators, if I was using this data structure, I'd have to return only the local data, which also then has some restrictions on what I can do with it. Since it's only the local data, I can't pass that into another operator that needs to do communication. But we were able to work it out in a natural way. And I can show how, even in the context of something as complicated as the Navier-Stokes equations for fluid dynamics, you could still use this style. But over time, I've evolved more towards having my coarrays outside of objects, or in some cases, having derived type coarrays. So I talked earlier about local coarrays and how there's an implicit synchronization at the end of a procedure. And then you can also, as I've talked about, have coarrays that are of a derived type. And this is really important in a library that I'm going to show you in just a moment that does task scheduling, where we want to have one scheduler image hand out tasks to a bunch of other worker images. And when those worker images finish their tasks, they have to post a payload in a mailbox that another image that can pick up for if it has a dependency on that data. So this is an example of a derived type coarray. Okay.
Damien, just a
yes.
quick, you've got 10 minutes left.
Thank you. Just briefly, this is so one of the things I love about this is that anyone who actually is familiar with the Navier-Stokes equations always recognizes this on the spot. And I want to say that this is not pseudocode. This is actual compilable Fortran syntax. And that level of expressiveness, I think, is really powerful. If this were written in the style of the heat equation solver that's in the tarball that you all have access to, then each of these objects, like P is the pressure in the fluid and U is the velocity in the fluid, would be local objects because all the communication happens in a separate data structure. If, like I just showed you, there was a coarray inside of these, then it would have to be the case that every time you return from applying an operator, you would only have local data, even though the object itself could be distributed. It turns out, if you work through it, that in this case, it works out okay, mainly because we're never passing something out to something that also has to communicate. So this is nirvana. These are user-defined, purely functional operators that could be operating on distributed objects, depending on how you define your coarrays. The last thing I want to cover, and I think I might, I'll skip over that last slide just in the interest of time. Well, I'll just mention very briefly here. This is that 1D burger solver that I talked about, the 400-line code. It's object-oriented, it's functional, it's using a coarray inside a derived type. And we were able to get over 80% parallel efficiency. So over 80% of what the ideal scaling would be out to 16,000 cores. And so one thing about this code is that this is a plot of execution time on the vertical axis, really image number on the axis going into the screen in this direction. But because our images are supported by MPI, it says MPI rank. And then on this axis, either a procedure or just a statement. And if you can read this, it's a synchronization point that is occupying the most time other than the main program, which is occupying all the time inclusively. So one disappointment with this code was that the bottleneck was synchronization. So if there were going to be any solution to improve the performance of the code, then we'd have to switch to an asynchronous approach, which would be a bit more complicated to program. And I did have one student who worked on a project with me where he did switch it to an asynchronous approach, and it didn't actually bias anything. So, which is one of the reasons I think it's good news that I showed you yesterday, that the most costly part of the heat equation solver that you have access to is actual floating point computation. It's the computing of the Laplacian, because I have a lot more hope that we can do a lot more to speed that up by doing things like offloading that do concurrent. Okay, so the last thing we're going to cover is events. And I have this Hello World example that takes Hello World to another level. And the basic idea is you can imagine each of these blue boxes as an image, and you can imagine each of these gold boxes as one element of a coarray. In this case, there's a greeting ready coarray where an image, let's say this is image 1 on the left and image n, or let's say image 3, I guess, on the right. Then the way this Hello World works, and this one is, I'm going to show you an animation here that's a bit more complicated than the one that I'm going to show you in code. With the more complicated one, at least I can explain it graphically, and then we'll simplify it down a bit when we get to the code. But the basic idea is that you can imagine each image is executing asynchronously at the beginning, so they might be at different points in the code. So the arrow here kind of indicating where it is and running where each image is and running the program. You know this is image 1 on the left here because you see the 1 in square brackets. Image 1 is going to query a coarray here where there's one element in this coarray for each other image, and it's an event type where the other image is saying, hey, my greeting's ready. I just printed a greeting. You can pick it up and print it. Okay. At the point when it queries it, maybe that other image hasn't created its greeting yet, so image 1 will move on. This is the value of not using synchronization, is that you don't, if there's other computation you can do, you query to see if the event has happened. If it hasn't, you can move on and do something else. You don't sit there and wait necessarily. So at some point in time, image 3 will post to its element. So this element, you can see down here, it goes from 2 to n because image 1 knows about its own greeting. So we don't need to have an element 1 here. So image 3 would be posting to its element saying, hey, my greeting's ready, you can grab it. Okay, but it won't wait after posting that information, it will move on. Okay. At some point, image 1, now in this Hello World, each image is going to create multiple, we're going to sort of loop around and create multiple greetings. You create one, image 1 picks it up, prints it. Now you overwrite that and create a new one. But once we've posted that we have it ready, there's really not much we can do in this simple Hello World. So now we'll have to wait for a signal that it's okay to overwrite that data. At some point, image 1 will come back around and query that element to see if that event has been posted. If so, it will grab it and print it, and now post back to image 3, hey, it's okay to overwrite that data. Okay. There are basically 3 statements. Well, let's see, 2 statements and 1 subroutine that you use with events in Fortran. There's event post, event wait, and there's also query. So event post and wait are image control statements. You can't use any image control statements inside of do concurrent. So there are constraints like that keep you from writing poor performing code. And when you query an event, you have to do so. It has to be something that's local that you're querying. And I believe that's a constraint in the language for performance reasons. So whenever possible, overlap communication and computation. Wherever possible, query without waiting. Those are just a couple of tips there. What is the event post doing? Well, it's actually incrementing an integer. It's called an atomic integer, but it's a private component inside the event type. So event type is something that you pull in from isofortran env, and then you can declare your event objects. The first one's allocatable because I don't know how many images there will be. The second one is static because I only need 1 per image. And event query just checks the count. You pass a count variable, and that gets defined when you call the subroutine. And then event wait decrements the count. Michelle?
Yeah, this event-driven stuff is really cool. Do you have any event-driven simulations?
Yes. So
Written with that? Okay.
Oh, well, depending on what you mean by simulation. So
Okay, but you were going to show us the event driven hello world.
Yes. Yes,
And
exactly.
then just to let you know, we've got
Yes, we're
3 more
we're
minutes.
at the end. Okay. So the basic idea of this, it's like the one that we just talked about, except that there's not the repeated looping to overwrite data that's been written. And so let's jump down to, you can see the use of block here. Block allows you to do some local declarations. And the basic idea is that I'm going to create this Coarray just as a regular array to indicate that which greetings have or have not been printed. I'll set all of the elements to true initially, and then image 1 is going to loop while there are any greetings that have not been printed. Inside that loop, it will loop over all of the other images. It's already printed its own image up here, and it will query the count, basically. The count gets initialized to 0. That's part of the language at the beginning. And every time it gets incremented, we know that that event has happened. Then we use event wait to decrement it back to 0. And then we can print the greeting. I think this is probably superfluous here because we know that the greeting's ready. So that's the basic idea of that. And I'll just exit here and flip back to my slides to see if there's anything to say to wrap up in our final minute. Shoot, I should have, okay, I won't bother trying to switch to present mode. Had we more time, I would explain this task scheduling framework. This is the only significant code that I've written that uses events. Wrote this with Brad Richardson and our collaborator / client at NASA Langley Research Center, Robert Singletary. Compilers are having a lot of problems with this code, and this was actually the code that inspired that workaround that I mentioned earlier that Brad came up with for two-sided communication. But basically, this allows us to have a scheduler image that hands out tasks to other images. And I guess you'll have to look through this in the slides. I haven't had a demo here to run for you that shows some task scheduling happening. Couple things are coming soon in Fortran, reductions in do concurrent, notified access, so you can put data on a remote image and then notify that image that it's there. And I think I'll leave it there then. Should I stick around for questions, or are we dropping off at 12:20?
Yeah, well, thank you so much, Damien. And thank you everyone for coming.